Hey guys, tonight we're going to travel back to a time just before our world truly began, to witness the birth of the first real human. Imagine, we are standing in the East African Rift Valley, 1.9 million years ago. The sun is a relentless white-hot disk in a vast sky. The landscape around you isn't the empty savanna you might picture. It's a vibrant, lethal world of acacia woodlands and sprawling grasslands, teeming with life that seems drawn from a fever dream. There are giant baboons, saber-toothed cats the size of lions, and clumsy, three-toed horses grazing in the distance. This is your planet, but it does not belong to you. But in that brutal landscape, a new figure appears, walking along the shore of a vast, shallow lake. From a distance, its stride is shockingly familiar. It's tall, upright, with long legs and arms that swing in a rhythm you recognize. This isn't a shuffling, ape-like creature. This is something new, something that carries itself with a purpose. This is your ancestor in a way you've never truly considered. Over the next 2 million years, an almost unimaginable stretch of time, this creature will be the first to walk out of Africa, the first to tame fire, the first to craft tools of profound symmetry, and the first to leave a deliberate mark on a seashell that we might dare to call art. It will spread across 3 continents, adapting and surviving through ice ages and supervolcanoes, becoming the true planetary pioneer. So who were they really? What was the internal spark, the unique combination of mind and body that drove them out of their cradle and across the globe? And how much of who we are today, our curiosity, our endurance, our very anatomy, was forged in the crucible of their world. Thanks to a century of searching for fossils, from the sun-baked earth of Kenya to the volcanic soils of Java, we can now piece together their story and walk with them on their incredible journey. Frankly, if you were dropped here in your pajamas, you wouldn't be a curious observer. You'd be a 2-minute appetizer for a dinophalis. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. That small click sends a big signal to the algorithm. That long-form, serious educational content still matters. And to me, it's an incredibly meaningful show of support. Thank you so much for helping keep this channel going strong. It always fascinates me to see where you're all tuning in from. Let me know in the comments where you are in the world and what time it is for you. Now, dim the lights. Maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. Before you can truly appreciate this new kind of hominin, this Homo erectus, you have to understand the messy family reunion they were born into. Evolution isn't a neat ladder, with one species graduating to the next. It's a tangled, thorny bush, with branches sprouting, twisting, and dying off all the time. For millions of years, this bush was dominated by a group known as the Australopithecines. You've probably heard of their most famous member, Lucy. For their time, they were a major success story. They were the first to commit fully to walking on 2 legs, a revolutionary adaptation that freed their hands. This is the bedrock of our lineage, the scientific evidence from fossils like Lucy that proved bipedalism came long before big brains. Walking upright was the first and perhaps most important step towards becoming human. But in every other respect, you would have seen them as distinctly ape-like. They were short, with long, powerful arms still suited for climbing trees, and they had brains not much larger than a modern chimpanzee's. Their faces were dominated by massive jaws, built to grind tough, fibrous vegetation. They were a brilliant adaptation for their world, but they were not us. The challenge for science has always been to pinpoint where that lineage, the one that led to you, truly begins. Drawing a line in the fossil record and saying, "Here, this is where ape ends and human begins," is one of the most difficult and contentious tasks in all of science. It's a bit like trying to decide the exact moment a color shifts from orange to red in a sunset. Early paleoanthropologists often had to deal with more immediate problems. In some parts of the world, their discoveries of large ancient hominin bones were met with local folklore about the bones of giants, requiring a delicate balance of science and cultural sensitivity. The entire Great Rift Valley is a geological marvel, a massive scar on the Earth's crust where tectonic plates are tearing Africa apart. For paleontologists, it's a gift, as this slow-motion separation has churned up and exposed ancient layers of Earth, revealing the bones of our ancestors that would otherwise be buried miles deep. It is the very definition of a cradle of humanity. And what it has revealed is that paleoanthropologists still argue fiercely over which fossil assemblages represent distinct species versus simple variations within one. Is that slightly thicker brow ridge or larger molar enough to name a whole new species? Or is it just the normal difference you'd find between any two individuals in a population? This is the fundamental puzzle that makes the period just before Homo erectus so fascinating and so maddeningly confusing. You wade deeper into this confusing ancestral soup, and the first characters you meet are the Australopithecines. As we said, they were defined by that one monumental trick, walking on two legs. But as you look closer, you see the compromises. Their bodies were a mosaic of old and new. They had human-like feet and a pelvis tilted for an upright gait, but their long, curved fingers and upward-pointing shoulder joints were straight out of an arboreal tree-climbing playbook. They lived a dual life, walking the land but likely retreating to the trees for safety or sleep. Their heads were conspicuously ape-like, with a small brain case sitting behind a forward-jutting jaw, a reminder that their world was still one of powerful chewing muscles, a life spent grinding down tough roots, tubers, and seeds. They were a successful and diverse group, a testament to the power of bipedalism. But they were a side branch, a brilliant experiment that ultimately wasn't going anywhere new. Then, out of this group, a new contender emerges. Around 2.4 million years ago, the fossils begin to change. The faces become a little flatter, the teeth a little smaller, and the brains, crucially, a little bigger. This is the one you've heard of. Homo habilis, the Handyman. The name was given for a very specific reason. Its bones were found alongside the first definitive stone tools. These weren't elegant weapons. They were crude, effective implements called Oldowan choppers. Imagine picking up a rounded river cobble and smashing it with another rock to knock off a flake or two, creating a brutally sharp edge. That was the extent of the technology. Simple, yet it was a profound breakthrough. For the first time, a hominin could carry a sharp edge with them, ready to slice meat from a carcass or crack open a bone for its rich marrow. This ability to process food outside the body was a game changer. The discovery of habilis and its tools was a landmark moment, thanks in large part to the tireless work of the Leakey family, Louis, Mary, and their son Richard, whose decades of searching in the blistering heat of Olduvai Gorge, Tanzania, literally unearthed the first chapter of the human story. But almost immediately, Homo habilis became a source of controversy. Louis Leakey was adamant that this was the first member of our own genus, Homo. He placed it at the base of our direct family tree. Yet many other scientists looked at the habilis skeleton and felt a sense of unease. Its brain, while larger than Lucy's, was still quite small. Its arms were long and its legs were short, proportions still reminiscent of an Australopithecine. Was it really a human, or was it just a clever ape? In fact, the very name Homo habilis was initially a subject of fierce debate. The quirky tidbit here is that some of his peers felt that simply making a crude tool wasn't a sufficient qualification to welcome habilis into the exclusive club of Homo. They argued it was too primitive, that it was, in essence, just a souped-up Australopithecus with a useful hobby. To make things even more confusing, another face appears in the crowd from the same time period. Homo rudolfensis. Known from a famous skull found on the shores of Kenya's Lake Turkana, formerly Lake Rudolph, this hominin presents a different puzzle. It had a significantly larger brain case than habilis, a trait that screams more human. But its face was surprisingly primitive, broad and flat, almost dish-shaped, reminiscent of the much earlier Australopithecines. Its teeth were also large and robust. So what was it? Was it a larger version of habilis, perhaps the male of the species? Or was it a completely separate lineage, trying out a different combination of features? The scientific evidence from microwear analysis on habilis teeth offers a clue to their lifestyle. The tiny scratches and pits on the enamel suggest a highly varied generalist diet. They were eating a bit of everything: leaves, fruits, and crucially, meat. But their powerful jaws show they still relied on tough, low-quality vegetation as a fallback. They were straddling two worlds, and so the picture you're left with is one of bewildering variety. For a period of several 100,000 years, the African savanna wasn't home to one aspiring human ancestor, but a whole caste of them. You might have seen a small band of gracile habilis scavenging a kill, while a stone's throw away, a group of more robust rudolfensis foraged for roots. Experts still debate whether rudolfensis is a separate species, the male of habilis, or something else entirely. This isn't a simple linear story. It's an evolutionary arms race, a period of intense experimentation where different hominin models were all competing on the same landscape, each with a slightly different toolkit of traits. And out of this creative, chaotic mess, one of them would stumble upon a blueprint so successful it would leave all the others behind in the dust. You're standing in this crowded room of ancestral ghosts, trying to pick out a familiar face. And then, suddenly, the crowd parts. About 1.9 million years ago, the fossil record stops whispering and starts to shout. At the site of Kubifora, a massive, sun-scorched expanse of badlands in Kenya that has yielded hundreds of hominin fossils, a skull was found that changed the entire conversation. Its official name is KNM-ER3733, a dry scientific label that masks its true significance. The quirky tidbit here is that this isn't a random code. It's the fossil's passport, meaning Kenya National Museum's East Rudolph, fossil number 3733. It's a catalogue number for a revolution. When you place this skull next to that of a Homo habilis, the difference is not one of degree, it's one of kind. The change is immediate and dramatic. Where the habilis skull is small and vaguely ape-like, this new skull is undeniably human in its architecture. The brain case is significantly larger, holding a brain that would eventually push towards 900 cubic centimeters, a huge leap in processing power. The face is smaller and flatter, tucked neatly beneath the forehead instead of jutting forward. The massive brow ridge is a signature feature, bold and straight like the brim of a cap. The teeth are smaller, the jaw less massive. It's a complete and total redesign. This wasn't a minor software update. This was a whole new operating system. Some scientists, noting the slightly more slender bones and thinner skull walls of these early African specimens, give them their own distinct name: Homo ergaster, the working man. They reserve the name Homo erectus for the later, more robust forms found in Asia. But this can sometimes obscure the bigger picture, making the family tree more complicated than it needs to be. For our journey tonight, we'll consider them all to be Homo erectus. From these earliest pioneers in Africa to their last descendants in Java, seeing them as one long-lived and variable species helps us appreciate the full, magnificent scope of their 2-million-year reign. And scientists still argue whether ergaster is a distinct African species that preceded Erectus, or simply an early regional variant of Erectus itself. What this new blueprint immediately tells you is that their lifestyle had fundamentally changed. A creature with smaller jaws and teeth isn't spending its days grinding tough, gritty plant matter. It has outsourced a huge part of the digestive process to technology. It's using those stone tools not just as an afterthought, but as a primary means of preparing food, slicing meat, pounding tubers, cracking bones. The changes went beyond the skull. Based on the shape of the ribs and pelvis, we can infer their entire torso was different. This is crucial scientific evidence. Homo erectus had a narrower, more barrel-shaped chest, which points to a smaller gut. An intestine is metabolically expensive tissue. By switching to a diet of high-quality, energy-dense foods like meat and marrow, they could afford to shrink their digestive system. That saved energy wasn't just wasted, it was rerouted to the most demanding organ in the body, the brain. This anatomical trade-off, a smaller gut for a bigger brain, was a pivotal moment in our evolution. It was the biological bargain that would ultimately make us human. This new hominin wasn't just a peeve ape that walked upright. It was a coordinated, efficient, and powerful new machine, a body and mind built for a new way of life. This blueprint wasn't just designed for surviving the dangers of the African savanna. It was a body built for walking clear over the horizon and doing something no other creature on this planet had ever done before. And for decades, the story of this new human blueprint was a purely African one. The script seemed simple. Homo erectus evolves in Africa, spends a few 100,000 years getting its act together, inventing better tools and growing a bigger brain. And only then, once it's fully equipped and ready, does it venture out to conquer the world. It's a logical, sensible story, and it is completely wrong. The moment you think you have the timeline figured out, the ground shifts beneath your feet, this time all the way to the foothills of the Caucasus Mountains in the modern Republic of Georgia. Here, beneath the ruins of a medieval Georgian village at a site called Dmanisi, archaeologists found something that broke all the rules. They found hominin skulls, and when they dated the earth around them, the results sent a shockwave through the world of paleoanthropology. The fossils were 1.8 million years old. Let that sink in for a moment. This isn't a few thousand years after their first appearance in Africa. This is a geological blink of an eye. You realize with a jolt that Homo erectus didn't wait around. They didn't have a long, quiet childhood in their African cradle. The ink was barely dry on their new evolutionary design before they were packing their bags. This wasn't a slow, tentative crawl out of the motherland. It was an explosion. Almost as soon as they existed, they were walking, generation by generation, following rivers, chasing herds, and pushing into a world no hominin had ever seen. They were thousands of miles from their origin point, living in a temperate climate that was a world away from the equatorial savanna. And here is where the story gets truly strange. When you look at the skulls of these Georgian trailblazers, you don't see the big-brained, physically imposing adventurers you might expect. The Dmanisi hominins are a shock. They were surprisingly small, some standing less than 5 feet tall, and their brains were tiny, clocking in at around 540 to 650 cubic centimeters. That's barely larger than the brain of Homo habilis. In fact, it's so small that if their skulls had been found in Africa without any context, they might have been dismissed as a primitive, dead-end species. And the scientific evidence from their toolkit hammers the point home. The stone tools found alongside them were the same kind of simple, older one-style choppers and flakes that habilis had been making for 500,000 years. They had not yet invented the more advanced Achulean handaxe. This creates a beautiful, maddening puzzle. If these first global pioneers didn't have big brains, and they didn't have advanced technology, what was their secret? What allowed them to achieve something so unprecedented? You look at their bones again, and the answer begins to reveal itself. They may have had small brains, but they had the new, efficient, long-legged Erectus body. They were built to walk, and to walk well. But their true advantage might have been something you can't see in a fossil at all. It might have been how they treated each other. Among the 5 skulls found at Dmanisi, one is a true scientific treasure. It belonged to an old individual, likely a male. But what's remarkable is that long before his death, he had lost all but a single tooth. His jawbone had completely healed over, meaning he lived for years in this state. This is the oldest, most powerful evidence for compassion in the human story. A toothless old man in a world of tough, raw food is helpless. He cannot chew. He cannot survive on his own. His survival is a testament to his group. They had to be finding him soft foods, marrow, brains, perhaps pounded meat or plants, and actively feeding him. They were keeping him alive. This incredible quirky tidbit is more than just a touching story. It suggests that the secret weapon of Homo erectus was the strength of their social bonds. They were a cohesive, cooperative group that cared for its vulnerable members. Perhaps that, more than any sharp rock or extra brain capacity, is what it took to walk out of Africa and begin the conquest of the planet. And as more fossils are unearthed from the site, archaeologists still argue whether the Dmanisi hominins represent a single, highly variable population caught at one moment in time, or are evidence of multiple distinct waves of migration out of Africa. The story is far from over. So, you stand there in your mind's eye, watching these small-brained, simply armed hominins leaving footprints in the Georgian soil, and the biggest question of all hangs in the air. Why? What possessed this particular creature, after millions of years of hominin evolution confined to Africa, to simply walk out of its homeland and keep on walking? The first thing you must do is banish any romantic notions of exploration. There was no Homo erectus Columbus standing on a hillside, pointing to the horizon and dreaming of new worlds. There was no conscious plan, no grand strategy. Their migration was an entirely unconscious process, a natural consequence of their success. It was less like an expedition and more like the slow, inexorable way that a stain of spilled wine spreads across a tablecloth. The most likely motive was the simplest one imaginable: lunch. Imagine your life as a member of a small Erectus band. Your world is defined by the herds. You follow the vast migrations of grazing animals: antelope, deer, ancient horses, because they are your walking pantry. Their movements dictate the rhythm of your life. When the herds move north into a new valley to find fresh grass, you move with them. It isn't a decision, it's an imperative. Generation after generation, this is the pattern. A group follows a herd, and as your own population grows, a small splinter group might follow a different herd, pushing just a little further. They don't know they are migrating. They just know that the food is that way. Over thousands of years, these small, incremental steps add up to a continental-scale expansion. This process wasn't happening in a vacuum. The world itself was urging them on. The Pleistocene epoch, the Great Ice Age, was a time of dramatic climatic instability. But Ice Age is a misleading term. It wasn't uniformly cold. It was a volatile series of glacial periods and warmer interglacials. During certain phases, the climate of Africa became drier, and the Sahara expanded, acting like a barrier. But during others, North Africa became greener, and the vast grasslands, the savanna ecosystem they were perfectly adapted to, expanded out of Africa and into the Middle East. This created a savanna pump, a biological corridor of familiar landscape, familiar plants, and familiar animals, stretching all the way to the gates of Asia. They weren't bravely venturing into a hostile, alien world. They were simply following their own world as it grew. The scientific evidence for this is written in the bones found at Dmanisi. Alongside the hominins, paleontologists found the fossils of African species like saber-toothed cats, short-necked giraffes, and giant ostriches. They didn't leave their ecosystem behind. They took it with them. Of course, this raises an interesting alternative. The quirky tidbit is that some researchers have proposed a coastal expressway theory. The idea is that instead of, or in addition to, following herds across the interior, some Erectus groups might have followed the coastlines out of Africa. A coastline is a fantastic resource, a linear, predictable buffet of shellfish, crabs, stranded fish, and edible seaweeds. It would have provided a reliable food source that could have drawn them step by step along the shores of the Red Sea, across the Arabian Peninsula, and on towards Asia. It's a compelling idea that might explain the sheer speed of their dispersal. Ultimately, their ability to move so far, so fast, wasn't down to one single advantage. It was their entire behavioral package. They had the long-legged, energy-efficient anatomy for walking. They had the basic tool-making skills to butcher any carcass they found. And as the Dmanisi elder shows us, they had the cooperative social structure to survive the inevitable hardships. This combination made them incredibly adaptable. They weren't just specialists of one environment, they were opportunistic pioneers, able to size up a new landscape and figure out how to exploit it. And so they spread. But historians still argue whether their dispersal was a single rapid event, a blitzkrieg across the continent, or a series of slower start-and-stop pulses over thousands of years, with populations moving, settling for a time, and then pushing forward once more. Whatever the pace, the die was cast. A human foot had stepped out of Africa, and the world would never be the same. You've followed their ghostly footprints out of Africa, but now it's time to look at the machine that made the journey possible. The body of Homo erectus wasn't just a slightly improved version of what came before. It was a radical departure, a new engineering solution for a new way of living. If you were to see an Australopithecus walking towards you, you would immediately recognize its ape-like heritage in its proportions. Short legs, a long torso, and dangling, powerful arms. But if you saw a Homo erectus at the same distance, stripped of its skin, you would say, "That's a human." They were the first of our ancestors to achieve modern, human-like body proportions, and this change was the key to their entire global success. The most spectacular proof of this comes from a single breathtaking fossil. In 1984, the famed fossil hunter Kamoya Kimeu, a key member of Richard Leakey's team, was walking along a dry riverbed near Lake Turkana in Kenya when he spotted a tiny, unremarkable-looking fragment of bone. It turned out to be the first piece of what would become one of the most important discoveries in human history, the Nariokotomi boy, more famously known as Turkana boy. What he and his team unearthed over the next few months was a nearly complete skeleton of an Erectus youth who died some 1.6 million years ago. He was not a jumble of disconnected bones, but a person, frozen in time. And what a person he was. His skeleton tells the story of this new body plan in exquisite detail. His arms are shorter, his legs are long and slender. His entire physique is linear and graceful. The quirky tidbit that startles everyone who learns about him is his height. Though analysis of his teeth shows he was just a youth, perhaps 8 to 11 years old, he already stood about 5 feet 3 inches, 160 centimeters, tall. Had he grown to adulthood, it's estimated he might have reached a towering 6 feet 1 inch, 185 centimeters, taller than many of us today. This wasn't a short, squat hominin. This was a tall, athletic creature built for striding across vast, open landscapes. There is a profound functional reason for this tall, lanky build. It's a perfect adaptation for staying cool in a hot, equatorial environment. Think of it as a biological radiator. More surface area relative to body mass means you can dissipate heat more efficiently. For a creature that was spending its days active under the punishing African sun, this was a crucial piece of engineering. You see the same principle in desert-adapted animals today. It's a body built not for the shade of the forest, but for the relentless exposure of the savanna. This physical revolution extended to every part of their anatomy. You see it in their teeth and jaws, which, as we've noted, became smaller and more delicate. This wasn't a random aesthetic choice. It's a direct reflection of their diet and technology. When you have stone tools to cut meat into manageable strips and pound tough plant tubers into a digestible pulp, you no longer need a massive facial structure built for heavy-duty grinding. The work has been moved from the jaw to the hands. Their entire head became more balanced, a control center sitting atop a mobile, efficient chassis. Perhaps the most crucial and subtle change was in the pelvis. This is powerful scientific evidence. The Homo erectus pelvis narrowed, becoming more compact and bowl-shaped. This was fantastic for efficient walking and running, stabilizing the torso and providing attachment points for the powerful gluteal muscles that drive us forward. But this efficiency came at a cost, a very high one. The birth canal became relatively smaller. At the same time, brains were getting bigger. This created an evolutionary crisis, an obstetrical dilemma. The solution was to give birth to babies earlier in their development, with smaller, less developed brains that could still fit through the narrowed passageway. The consequence of this is profound. Homo erectus babies were born utterly helpless, requiring a long period of dependent childhood while their brains finished growing outside the womb. This single anatomical shift fundamentally rewired their social lives, demanding long-term parental care, cooperative child-rearing, and a stable group structure to protect these vulnerable young. It was the biological origin of the human family. And yet, even with a skeleton as complete as Turkana boy's, mysteries remain. Scientists still argue whether his growth rate was more ape-like and rapid, meaning he was older than we think, or if it followed a more human-like, slow and prolonged trajectory. He is a perfectly preserved question, written in bone. That tall, linear body, with its long legs and balanced torso, wasn't just built for walking efficiently. It was built for a specific, revolutionary form of locomotion. A chimpanzee, for all its immense upper body strength, is a clumsy and inefficient biped. It can certainly outsprint you over a short distance. But if that race is a marathon, you would leave that chimp in the dust, and every other primate with it. In fact, over a long enough distance, a fit human can outrun almost any animal on the planet. This extraordinary ability, this superpower of endurance running, was born with Homo erectus. It is one of the most profound and defining legacies they have given us. Your new body is a masterpiece of engineering for this single purpose. Remember that newly shaped pelvis? It's narrower and more compact, providing stability and preventing your torso from pitching wildly from side to side as you run. Your gluteus maximus, your butt muscle, is now the largest muscle in your body, not just for looks, but to act as a powerful engine, driving your legs forward and keeping you upright. A tough rubbery band of tissue in your neck, called the nuchal ligament, acts like a natural passive shock absorber, keeping your head stable and your gaze fixed on the horizon as you lope along, something a chimpanzee simply cannot do. And in your legs, long Achilles tendons stretch and recoil with every stride, acting like powerful springs, storing and returning energy, making your gait incredibly efficient. Now, put yourself in their bare feet. The sun is at its zenith, beating down on the savannah with a heat that sends most animals seeking shade. But you are out in it. Your target is a kudu, a large antelope. You don't try to sneak up on it or outsprint it. That would be a fool's errand. You simply get it moving, forcing it into a gallop, and then you follow at a steady, relentless trot. The kudu is faster, and it quickly disappears from view. But you don't stop. You follow its tracks, jogging, jogging, always jogging. Eventually you crest a rise, and there it is. It has stopped, thinking the danger has passed. When it sees you, a strange, persistent creature still on its tail, it panics and bolts again. This is the deadly rhythm of the persistence hunt. The animal sprints, using its anaerobic capacity, and then it must stop to recover. You just keep coming, using your supremely efficient aerobic system. The crucial difference is in how you handle the heat. The kudu is starting to struggle. It's covered in a thick coat of fur, and its only way to cool down is to pant. The quirky tidbit that separates you from almost all other mammals is that you can sweat, using your entire body as a radiator. As the chase continues for miles, for hours, the kudu's body temperature climbs higher and higher. It is galloping towards a lethal case of hypothermia. Finally, it stumbles, slows, and collapses. It hasn't been speared or cornered. It has been run to death. This isn't just a fantasy. This technique, persistence hunting, has been documented as a mainstream historical fact into the modern era among groups like the San people of the Kalahari, providing a living example of this ancient strategy. And it's not just a modern human skill. Scientific evidence from mathematical models of Erectus biomechanics confirms their skeletons were beautifully adapted for this kind of marathon-style running, suggesting they could have maintained a steady pace for hours on end. Now, this vivid picture leads to a major question. Anthropologists still argue whether persistence hunting was a primary strategy or an occasional tactic for acquiring meat. Was it their go-to method, or a desperate fallback plan for when other opportunities failed? But as you stand over your exhausted prey, the central problem of this strategy becomes blindingly obvious. You've been jogging for hours under a sun that can bake the earth as hard as pottery. You should be the one collapsing. There is one final crucial adaptation you would need to pull this off. A change that would alter your appearance more profoundly than anything else. To survive this kind of exertion, you need a cooling system, unlike anything the world has seen before, and that means getting rid of your fur. You simply cannot be a world-class marathon runner in a fur coat. It's a thermodynamic impossibility. The incredible engine of your new Erectus body, capable of running prey to the point of collapse, generates a catastrophic amount of internal heat. If you were still covered in the thick pelt of your Australopithecine ancestors, a persistence hunt wouldn't end with a meal. It would end with you boiling in your own skin, collapsing from heat stroke long before your prey. The fur had to go. It was a thermodynamic death sentence, and evolution's only solution was to throw off the blanket entirely. And in its place, you develop a cooling system of unparalleled genius. Your skin becomes a massive living radiator. Millions of tiny eccrine sweat glands emerge across its surface, each one a microscopic cooling tower. As you run, your body pumps out salty water, and as it evaporates in the dry savanna air, it carries away your excess heat, keeping your core temperature stable. This is your critical advantage. While the fur-covered kudu can only pant, desperately trying to vent heat from its mouth and tongue, you are sweating from your head to your toes, a far more efficient and sustainable method of thermoregulation. You have, in effect, become a water-cooled machine, a perfect adaptation for an active life under the equatorial sun. But solving one problem in evolution almost always creates another. By shedding your protective layer of fur, you have exposed your bare skin to a new and insidious danger, the sun itself. Specifically, you've exposed it to the relentless bombardment of ultraviolet radiation. UV rays are more than just a recipe for a bad sunburn. They are a destructive force. They penetrate the skin and destroy a vital nutrient in your blood called folate, or vitamin B9. This is a huge problem. Folate is absolutely essential for proper cell replication, and, crucially, for healthy fetal development. A lack of folate can lead to devastating birth defects like spina bifida. For a species to survive and reproduce, it must protect its folate levels at all costs. So, evolution provides a new shield. Your skin begins to produce copious amounts of a dark pigment called melanin. Specialized cells called melanocytes work overtime, pumping this pigment into the upper layers of your skin, creating a natural, biological sunblock. This melanin barrier is incredibly effective at absorbing and scattering harmful UV rays before they can penetrate deeper and destroy your precious folate. The scientific evidence for this is now written directly into our own DNA. By studying the MC1R gene, which acts as a master switch for melanin production, geneticists have determined that the specific genetic variants responsible for dark skin became fixed in the human population around 1.2 million years ago. The timeline is a perfect match. The moment Homo erectus became a naked, endurance-running hunter on the savannah is the moment dark skin became a non-negotiable, essential adaptation. The quirky tidbit here is that you haven't actually lost your hair. You still have the same number of hair follicles on your body as a chimpanzee does. The genetic change wasn't an instruction to delete the follicles, but to change the type of hair they produce. Instead of the thick, long, coarse terminal hair that makes up a chimp's coat, most of your follicles now produce Velu's hair, the fine, short, barely visible peach fuzz that covers your body, allowing sweat to evaporate unimpeded. The relationship between UV exposure and skin pigmentation is now a mainstream historical fact of human adaptation. Across the globe, the skin color of indigenous populations correlates almost perfectly with the intensity of UV radiation in their ancestral homelands. And so, a profound transformation is complete. Imagine this creature now, tall, athletic, and long-limbed. Utterly naked, save for the hair on its head to protect its brain from the direct overhead sun. And its skin is a deep, rich brown, shimmering with a fine sheen of sweat. This is a pivotal moment in our story. For the first time, an ancestor looks back at you with a face and a form that is undeniably, fundamentally human. It's a beautiful, powerful image, but it also raises a delicate question. Researchers still argue about the precise timeline for these changes, and whether hair loss fully preceded the evolution of dark skin, or if the two adaptations happened concurrently in a more gradual and overlapping process. Whatever the exact sequence, the end result is the same. Standing there on the African savanna, you see a creature that is no longer an ape that walks on two legs. You see a human, forged in the heat of the sun, ready to take on the world. This new body, this naked, sweat-cooled, distance-running machine, is the platform upon which the real revolution will be built. For all its elegant efficiency, the body is just the hardware. The true upgrade, the one that will ultimately change the destiny of the planet, is happening inside the skull. The brain of Homo erectus is undergoing an expansion so rapid and so profound that it has no precedent in the history of life on Earth. You have to remember where they started. Those early pioneers you met in Dmanisi, Georgia, were walking around with brains of about 600 cubic centimeters, a respectable size, but not a huge leap from their habilis-like ancestors. But now, you fast forward just 500,000 years, a mere blip in evolutionary time. You travel east to the island of Java in Indonesia. Here, in 1969, a skull known as Sangairan 17 was pulled from the earth. It was a classic Homo erectus, robust and thick-boned, but its brain case tells a stunning story. It held a brain of nearly 1,200 cubic centimeters. In the grand scheme of things, they had nearly doubled their brain volume, pushing them right up to the lower edge of the modern human range, which averages around 1,350 cubic centimeters. This explosive growth begs a simple critical question. How? A brain is the most greedy, power-hungry organ imaginable. This is the core of the expensive tissue hypothesis. Your brain, right now, as you're listening to this, is using about 20% of your body's total energy budget, even though it only accounts for about 2% of your body weight. It is a metabolic furnace. You cannot simply decide to evolve a bigger brain any more than you can decide to put a V8 engine in a go-kart and expect it to run without changing the fuel tank, the chassis, and the cooling system. Evolution is a ruthless accountant. The energy books must be balanced. To afford the staggering cost of a bigger brain, Homo erectus had to find the energy somewhere. They did it in two ways. They cut costs elsewhere, and they massively increased their income. The cost-cutting came from the gut. As we saw, their torsos were becoming narrower, their guts smaller. A large digestive tract is also expensive tissue, needed to slowly break down tough, low-quality plant foods. By switching to a richer diet, they could afford to shrink the gut, and the energy saved was immediately reallocated upstairs to the booming neurological metropolis in their head. The income part of the equation came from that new diet. Meat, fat, and marrow are the most energy-dense foods in nature. The successful coordinated hunting we imagined earlier wasn't just for a celebratory feast. It was the essential fuel source that paid for this cerebral expansion. It created a powerful feedback loop. A slightly better diet provides energy for a slightly bigger brain, which in turn allows for cleverer hunting strategies and better tools, which leads to an even better diet, and so on. The quirky tidbit about this cerebral expansion is how evolution managed to pack all this new hardware into the same limited space. As the brain grew, it couldn't just expand like a balloon. The solution was to start folding it. The smooth surface of an early mammal's brain began to wrinkle and crease, forming the distinctive pattern of ridges, gyri, and valleys, sulci, that you recognize as a human brain. It's an ingenious packing solution, like taking a large sheet of paper and crumpling it up to fit inside a small ball, massively increasing the surface area, the cerebral cortex where the real thinking happens, without needing a skull the size of a watermelon. And what did they do with all this new processing power? The cognitive benefits were staggering. A larger brain meant a better memory, the ability to store a detailed mental map of a huge territory, the location of waterholes, the seasonal movements of herds, the places where the best tool-making stones could be found. It meant better planning, the ability to think ahead, to conceive of a symmetrical handaxe within a rough cobble, and to execute the dozens of sequential steps needed to create it. And crucially, it meant better social processing. A big brain isn't just for understanding the physical world. It's for understanding the social world, for navigating the complex web of alliances, rivalries, friendships, and obligations within a larger, more cooperative group. The scientific evidence from their skulls hints at this, in the form of endocasts, natural impressions of the brain's surface left on the bone's interior. These show that Broca's area, a region vital for language production and complex planning in modern humans, was already well developed in Homo erectus. The wiring for a more complex mind was being laid down. Of course, the story is never simple. Neuroscientists still argue whether brain size or brain organization was the more critical factor in the cognitive leap of Homo erectus. Was it simply that they had more neurons, or was it that those neurons were being connected in new, more efficient, and more creative ways? That ravenous, expanding brain demanded payment. You cannot run a neurological superpower on a diet of fibrous plants and the occasional lucky lizard. The feedback loop connecting diet and intellect required a steady, reliable, and incredibly rich source of calories and protein. For a long time, the prevailing image of our early ancestors was that of timid scavengers, skulking at the edges of a lion kill, waiting for the big predators to finish so they could dash in, grab a few scraps of leftover meat, and flee. But the evidence that Homo erectus left behind in the scattered refuse of their meals paints a very different and far more formidable picture. They were not just scavengers. They were hunters, and they were lethally good at it. Across Africa and Eurasia, archaeologists have found sites that can only be described as ancient butcheries. These are not random collections of bones. You find the remains of enormous animals, creatures that even a modern human armed with a rifle would think twice about confronting. We're talking about giant, thick-skinned elephants, hippos with their formidable tempers and formidable teeth, and even the colossal, extinct buffalo Paleolithic, whose horns could span 10 feet from tip to tip. And lying amongst these scattered bones, you find their stone tools, the Achulean Handaxes and sharp flakes they used to dismantle these mountains of meat. The smoking gun, the piece of forensic evidence that elevates them from scavenger to predator, is found in the microscopic scratches on the bones themselves. When you look at a fossilized bone under a powerful microscope, you can often see two different kinds of marks: the deep, rounded grooves left by a carnivore's teeth, and the fine, V-shaped striations left by a stone tool. The crucial question is, who got there first? At these Homo erectus sites, the answer is clear and consistent. The stone tool cut marks are frequently found underneath the carnivore tooth marks. This means the hominins were getting to the carcass first. They were carving off the prime cuts, the massive haunches and racks of ribs, and only after they had taken their fill did the hyenas and jackals move in to gnaw on the leftovers. They had primary access to the most nutritionally dense parts of the animal. Imagine the scene. A small band of maybe a dozen hunters. They've used their persistence hunting ability, their cunning, or perhaps a coordinated, terrifying charge to isolate and bring down a giant buffalo. The air is thick with the coppery smell of blood and the sounds of labored breathing from the dying animal. There is no time to waste. The scent will soon draw every predator for miles. They work quickly, with an practiced efficiency. Some use heavy hand axes as cleavers to dismember the limbs, while others use razor-sharp flakes to slice through the thick hide and carve away slabs of muscle. It's a scene of immense cooperation, courage, and planning. A world away from a lone chimp bashing a nut with a rock. A successful kill like this would provide tens of thousands of calories, enough to feed the entire group for days or even weeks. A massive return on their investment of energy and risk. In some places, their hunting appears to have been shockingly systematic. The mainstream historical fact is the site of Olorgesailia in Kenya, which contains a massive and mysterious accumulation of over 1,000 fossilized baboons, many of them found with Homo erectus tools. It has been interpreted by some as evidence that these hominins were capable of surrounding and systematically slaughtering entire troops of primates. The scientific evidence from isotopic analysis of their fossilized teeth confirms this dietary shift in a different way. By measuring the ratios of certain chemical isotopes in the tooth enamel, scientists can reconstruct their diet, and the signature for Homo erectus points to a significant and sustained increase in meat consumption compared to their predecessors. And they didn't just eat the meat. The quirky tidbit is their focus on a hidden, protected resource: bone marrow. After smashing open a large femur with a rock, they could scoop out the fatty, calorie-dense marrow inside. This was a food source almost completely inaccessible to predators like lions or hyenas, who lacked the dexterity to get at it. It was like a locked pantry of pure energy, and Homo erectus had the key. Of course, the details of their methods are still fuzzy. Archaeologists still argue over the exact hunting methods used, whether they relied more on sharpened wooden spears, clever traps, or the terrifying spectacle of driving entire herds of animals off cliffs. But whatever the specific techniques, the conclusion is the same. This new, reliable stream of high-energy fat and protein was the fuel that fed the fire of the burgeoning human mind. Without the hunt, there is no us. The hunt provided the fuel, but you cannot dismantle an elephant with your bare hands and teeth. The success of Homo erectus as a predator was entirely dependent on their technology. For nearly 1 million years, the hominin toolkit had been a simple, brutish affair. The older one, chopper. It was a tool of convenience. You pick up a suitable rock, you smash it with another, and a sharp flake comes off. You now have 2 tools: the sharp flake for cutting, and the core rock, or chopper, for smashing. It was effective, but it was thoughtless. There was no design, no artistry, no sense of a preconceived form. It was a purely subtractive process, about getting a sharp edge with a minimum of effort. Then, around 1.7 million years ago, coinciding with the rise of these large-brained, efficient hunters, something new appears in the dust of the African Rift Valley. It is a tool so different, so advanced, that it signals a genuine revolution in the way our ancestors thought. This new invention is the Achulean Handaxe. At first glance, it might not look like much. A teardrop-shaped piece of stone, sharpened on all sides. But you must understand, the leap from an Oldowan chopper to an Achulean Handaxe is as significant as the leap from a log raft to a steamship. The chopper was a found object, slightly modified. The Handaxe is a created object, meticulously sculpted. It is a tool that has been worked on both sides, a technique called bifacial flaking. It is symmetrical, often beautifully so, with a pointed tip and a rounded base designed to fit comfortably in the palm of your hand. The profound difference is a conceptual one. To make an Oldowan chopper, all you need to understand is cause and effect. I hit this rock, a sharp piece comes off. But to make an Achulean Handaxe, you have to possess a quality of mind that is leagues more advanced. You have to be able to look at a large, shapeless lump of flint or basalt and see, in your mind's eye, the finished, symmetrical form hiding within it. You have to have a mental template, a design. The tool exists in your imagination before it exists in your hand. This is the imposition of an abstract idea onto the physical world. This is the birth of design. The process itself was a complex, multi-stage operation. It required dozens, sometimes hundreds, of precise strikes. The toolmaker, the flint napper, would first have to select the right kind of raw material, understanding its internal structure and how it would fracture. Then, using a hard hammerstone, they would perform roughing out work, knocking off large flakes to establish the basic shape. After that, they might switch to a softer hammer, perhaps a piece of bone or antler, to allow for finer, more controlled flaking, thinning the edges and refining the symmetry. The scientific evidence for the complexity of this process comes from modern flint napping experiments. When archaeologists try to replicate these tools, they find it requires enormous skill, training, and a deep, intuitive understanding of fracture mechanics. It is not a skill you can learn in an afternoon. It's a craft that would have been passed down and perfected over generations. The mainstream historical fact is that the industry is named Achulean after Saint-Achul, a suburb in northern France where these tools were first found and identified in the 19th century, and they are found everywhere. This wasn't a local fad. It was a cultural and technological phenomenon that spread across Africa, Europe, the Middle East, and India. The quirky tidbit is their sheer, baffling abundance. At some sites, millions of hand axes have been found, far more than would be needed for simple butchery. Some are oversized and beautifully crafted, but show no signs of use, leading to wild speculation. Were they a form of prehistoric currency? A display of a male's fitness and skill to attract a mate? A ritual object? This global success makes one geographical anomaly all the more puzzling. In East Asia, in places like China and Indonesia, where Homo erectus thrived for over 1 million years, Achulean handaxes are almost entirely absent. The hominins there continued to use simpler chopper-style tools. This distinct technological boundary is known as the Movius line, and experts still debate why some Homo erectus populations in East Asia never adopted Achulean technology. Did the first migrants leave Africa before the handaxe was invented? Did they find that other materials, like the plentiful bamboo in Asia, were more suitable for making the sharp tools they needed, making complex stone axes redundant? Or were they just separated for so long that they developed their own distinct cultural traditions? The Handaxe, this simple piece of shaped stone, is not just a tool. It is a fossilized idea, a window directly into the mind of its maker, and it tells us that the lights, for the very first time, were truly on. You hold the finished Handaxe in your mind, feeling its weight, its sharp edges, its perfect, pleasing symmetry. This object is far more than a simple tool for butchering an animal. It's a piece of fossilized thought. It is the clearest window we will ever have into the cognitive world of Homo erectus, and it tells us that a profound and revolutionary change has happened in the landscape of their minds. The existence of this tool is direct proof of abstract thought. The symmetrical teardrop shape did not exist in the rough cobble of flint until a mind conceived of it and, through patient, skilled effort, imposed that idea onto the raw material. This is the essence of creation. It demonstrates a capacity for planning and foresight that was simply absent in their ancestors. The flint knapper couldn't just randomly bang rocks together. They had to follow a specific operational sequence, a mental checklist of steps. They had to think ahead, not just one step, but 2, 3, 10 steps into the future. If I strike the core here with this much force, a flake of this shape should detach, setting me up for the next strike over there. They also had to be adaptable, to problem solve on the fly. If the stone had a hidden flaw, or if a flake broke off in an unexpected way, they had to adjust their entire plan to salvage the tool. This is complex, sequential thinking, the same kind of cognitive architecture you use to follow a recipe, assemble furniture, or plan a journey. Then there is the question of its sheer artistry. Many of these handaxes are far more symmetrical and beautifully finished than they need to be for purely functional purposes. You can make a brutally effective cutting tool with just a few strikes. But they didn't. They would spend extra time and effort taking off dozens of tiny, delicate flakes to refine the shape, to make the edges perfectly straight and the overall form flawlessly balanced. Why? Does this suggest a nascent sense of aesthetics? An appreciation for symmetry, beauty, and form for its own sake? The quirky tidbit that fuels this speculation is a single extraordinary handaxe found in Britain, dating back some 400,000 years. It's oversized and seemingly impractical for daily use, but it was crafted from a stunning piece of flint with a fossil sea urchin perfectly preserved in its center, its 5-fold symmetry directly aligned with the tool's point. It's almost impossible to believe the napper didn't see this, appreciate it, and deliberately shape the tool to feature the fossil. Was this the first piece of art? A tool imbued with meaning beyond its function? This leap in manual dexterity and planning has a fascinating and direct link to another key human trait: language. The scientific evidence here comes from our own brains. Modern fMRI studies, which scan the brains of people as they learn to make Achulean tools, show that the process activates the same neurological circuits we use for language, particularly Broca's area. The parts of the brain that control complex, sequential hand movements are intimately interwoven with the parts that control the complex, sequential muscle movements of the lips, tongue, and larynx to produce speech. It's possible that the very act of making these tools, and crucially, of teaching others how to make them, was a driving force in the evolution of language. It's hard to imagine a master napper teaching an apprentice through grunts and pointing alone. They would have needed some form of proto-language, a way to say, "Not there, here. Hit it softer. Watch this." The hand and the tongue may have evolved together in a feedback loop of increasing complexity. The design of the Handaxe became so successful, so ingrained, that it persisted for an incredible length of time. The mainstream historical fact is that the basic Achulean Handaxe design remained the dominant hominin technology for over 1,000,000 years, making it by far the longest used tool in human history. Its stability is a testament to its effectiveness and to the power of cultural transmission. But even so, we are left with a tantalizing debate. Anthropologists still argue whether the extreme symmetry of some handaxes served a functional purpose or was purely a result of cultural tradition and aesthetics. One practical theory suggests that a symmetrical tool is more aerodynamic, making it a more effective projectile when thrown at prey. Others argue that this is projecting our own modern sensibilities onto the past, and that the symmetry is simply a natural byproduct of the bifacial flaking technique. But when you look at the best of their work, it's hard not to feel that you are in the presence of not just a tool maker, but a craftsman, an artist, a mind that was beginning to appreciate the world, not just for what it could provide, but for what was beautiful. So you have this masterfully crafted object, a testament to a new kind of mind. But what did you actually do with it? The answer seems to be almost everything. The Achulean Handaxe wasn't a specialized tool for a single task. It was the original multi-tool, the Paleolithic Swiss Army knife. Its pointed tip was perfect for piercing thick hides or breaking open joints. Its long, sharp edges were ideal for slicing meat or scraping hides clean. The heavy, rounded base could be used as a hammer to smash bones for their marrow or to pound plant fibers. You could use it to dig in the earth for edible tubers or to find a source of water. You could even use it to chop wood, shaping a branch into a digging stick or a rudimentary spear. In a pinch, the tool itself could serve as a core, where you could strike off a small, razor-sharp flake for a more delicate cutting task. It was an all-in-one solution for survival. This naturally leads to the quirky tidbit of modern experimental archaeologists who, in their quest to understand the past, have spent countless hours trying to replicate its uses. They've butchered roadkill, chopped down trees, and yes, even tried throwing handaxes at targets. The results of these projectile experiments are hilariously mixed, leading to an ongoing debate over whether they were ever really used as thrown weapons, or if they were simply too valuable and heavy to risk flinging into the bushes after a fleeing animal. The best scientific evidence for their function comes from a less dramatic but far more conclusive source: use-wear analysis. By examining the edges of ancient handaxes under powerful microscopes, researchers can identify the subtle patterns of polish, chipping, and striations left behind by different activities. The microscopic signature of cutting meat is different from that of scraping wood, which is different from that of digging in silica-rich soil. And the analysis confirms it all. These tools were used for a vast range of tasks, on a variety of materials. Of course, this highlights a massive preservation problem. We have millions of stone tools because stone survives for millions of years. But what about the tools they made from less durable materials? Wood, bone, antler, and hide would have been essential parts of their technological world. But these organic materials rarely survive the ravages of time. A wooden spear or a bone knife, left on the savannah, would rot or be gnawed away to nothing in a matter of years. We are looking at their world through a keyhole, seeing only the indestructible stone and bone fraction of their culture. But every now and then, a miracle of preservation gives us a glimpse into this lost world. In a coal mine in Schöningen, Germany, a set of wooden spears was discovered, preserved for 400,000 years in waterlogged soil. Now, these were likely made by a descendant species, Homo heidelbergensis, but there is no question that Homo erectus, the inventor of the Handaxe, was more than capable of the same craftsmanship. And these weren't just pointy sticks. The mainstream historical fact is that the Schöningen spears are so perfectly balanced, with the weight concentrated at the front like a modern tournament javelin, that they reveal a stunningly sophisticated understanding of ballistics and aerodynamics. This wasn't just tool use, it was engineering. And from Olduvai Gorge, the cradle of so much of our history, comes an absolutely stunning barbed bone point. It's a delicate, precisely worked object that would have been lethally effective on the tip of a spear or harpoon. It shows a level of artistry and skill with bone that rivals anything they accomplished in stone. This evidence of spears and points made from other materials forces us to reconsider the Handaxe itself. We picture them holding it directly in their hand. But was that always the case? Experts still argue whether Homo erectus hafted their hand axes onto wooden handles or always used them handheld. Attaching one to a handle would turn it into a formidable axe for chopping wood or a devastating weapon, but finding definitive proof of handles from 1,000,000 years ago is next to impossible. What is clear, however, is that you are looking at a creature with a comprehensive and adaptable toolkit, fully capable of shaping its world from wood, bone, and stone. You have the body of a hunter and the mind of a craftsman. You have a toolkit that can dismantle a beast the size of a car. But there is one final piece of the puzzle. One more technological leap that would take all of your other advantages, your big brain, your cooperative group, your high-quality diet, and pour gasoline on the fire of your evolution. Literally. That technology is the control of fire itself. It's an idea so powerful, so elegant, that for many thinkers, it's the single key that unlocks the entire mystery of what made us human. The most famous champion of this idea is the primatologist Richard Wrangham, and his cooking hypothesis is a thing of beautiful simplicity. His argument is that the most important evolutionary event in our lineage wasn't the creation of the first stone tool, but the taming of the first flame. Cooking, he argues, is a form of pre-digestion. When you apply heat to food, you fundamentally change its structure. Tough, collagen-filled meat becomes tender and falls apart. The rigid cellulose walls of plant cells break down. Complex starches are gelatinized into a form your body can easily absorb. In essence, you are using the fire as an external stomach, doing much of the hard digestive work before the food even passes your lips. This simple act would have had revolutionary consequences for your energy budget. Raw food is hard work. A chimpanzee might spend half its waking hours just chewing. But by cooking your food, you drastically reduce the amount of time and energy needed for mastication and digestion. More importantly, you dramatically increase the amount of energy you get out of the food. Cooked meat provides more net calories than raw meat. Cooked tubers provide vastly more than their raw, often indigestible counterparts. Cooking also neutralizes toxins in many plants, opening up a whole new menu of edible resources. And it kills parasites and bacteria, reducing the disease load and making you healthier. This is the perfect solution to the expensive tissue problem we talked about. This flood of easily accessible high-quality energy is exactly what you would need to fuel that greedy, growing brain, while simultaneously allowing your gut to shrink even further. It's the ultimate feedback loop. Fire lets you cook. Cooking gives you more energy. More energy lets you grow a bigger brain. And a bigger brain is smart enough to get even better at controlling fire and hunting. It's a theory that ties everything together in one neat, compelling package. But the benefits of fire go far beyond simple nutrition. Imagine your world before fire. Your day is dictated by the sun. When darkness falls, your world shrinks to the range of your immediate senses. The night is cold, and it is filled with predators whose eyes are far better than yours. You are vulnerable, huddled together for warmth and safety. Now, introduce a campfire. The darkness is pushed back. The flickering circle of light becomes a zone of safety, a magical barrier that the saber-toothed cats and giant hyenas are reluctant to cross. The cold of the night is replaced by a comforting warmth. The fire becomes the center of your social world. It's a place to gather after the hunt, to share food, to mend tools, to watch the children. It extends your usable day, providing light for social interaction and technological work long after the sun has set. It's around the hearth that complex social bonds are forged, that stories might be told for the first time, that culture is truly born. The mainstream historical fact is that the earliest, most widely accepted and undeniable evidence for the controlled use of fire comes from a site in Israel called Gesher Benot Yaakov, dated to about 780,000 years ago. There, archaeologists found distinct hearths with clusters of burned seeds and flint. It's an open and shut case. But that's much later than the big brain expansion really takes off. More tantalizing is the scientific evidence from Wonderwork Cave in South Africa, where microscopic traces of burned bone and plant ash have been found in layers dated to a stunning 1 million years ago. This is a much better fit for the timeline, but the evidence is more ambiguous. The quirky tidbit is that our ancestors were likely fire scavengers long before they were fire makers, opportunistically using the flames from natural wildfires, started by lightning strikes to cook food or ward off predators, a crucial first step in overcoming a natural fear of flames. It's a powerful theory, one that seems to explain everything so perfectly. It gives you warmth, safety, more energy, better health, and a social centerpiece all in one go. It's the invention that makes us human. It's a beautiful story. But there is a major problem with it, a very, very big one. The problem is one of time. The timeline is all wrong. Your beautiful, elegant cooking hypothesis, the one that explains everything so perfectly, crashes headfirst into the stubborn, inconvenient reality of the archaeological record. The first undeniable, widely accepted evidence for controlled fire is from 780,000 years ago in Israel. The more tantalizing but still debated evidence from Wonderwork Cave might push that back to 1 million years. And yet, Homo erectus was living in Dmanisi, Georgia, 1.8 million years ago. Their brains were already well on their way to doubling in size long before that. They had walked out of Africa, populated vast swaths of Asia, and adapted to climates far cooler and more seasonal than their equatorial homeland. All, it seems, without a campfire to huddle around. This chronological mismatch is a gaping hole in the story. It forces you to ask a very difficult question. What if fire wasn't the primary driver we think it was? What if this incredible creature accomplished all of these world-changing feats in the cold? Try to imagine that life. Imagine a winter in prehistoric Georgia, where temperatures would have regularly dropped below freezing. How do you survive the night, naked and without a flame? How do you keep a helpless, slow-growing infant from freezing to death in the darkness? This is not just a theoretical puzzle, it's a stark question of biological survival. You have to start exploring the alternatives. Perhaps the most obvious solution is clothing. The quirky tidbit is that while the idea of Homo erectus draped in simple animal hide cloaks is entirely speculative, no prehistoric tailoring has survived 1,000,000 years. It is a logical and plausible inference. After butchering an animal, using a sharp flake to scrape the skin clean, and then simply wrapping it around your body for insulation is not a huge cognitive leap. It's a simple, effective solution. Maybe they found shelter in caves, packing their bodies tightly together through the long, cold nights, sharing body heat like penguins in a blizzard, a writhing mass of humanity waiting for the sun. Another possibility is that their biology was simply different from ours. They may have had a much higher basal metabolic rate, their internal furnaces burning hotter than ours do, generating more passive body heat at the cost of requiring even more calories to fuel it. Maybe they were just, for lack of a better word, tougher, more resilient, more inured to the cold, with a physiological tolerance for hardship that our comfortable, centrally heated modern bodies can barely comprehend. The mainstream historical fact is that later hominins who lived in cold climates, like the Neanderthals, had clear anatomical adaptations for the cold, such as a stocky, heat-conserving body shape and wide nasal passages to warm the frigid air they breathed. Homo erectus, with their tall, linear, heat-shedding bodies, had no such features. They were tropical creatures, and yet they managed to survive in temperate zones. This forces us to reevaluate everything. Maybe the cooking hypothesis is only half the story, a later innovation that accelerated a process already well underway. The ambiguous scientific evidence from sites like Fora in Kenya, where patches of baked earth have been dated to 1.5 million years ago, keeps the dream of earlier fire alive. But you cannot tell from a patch of baked clay if it was a deliberately controlled hearth or simply the spot where a lightning-struck tree stump smoldered for a week. And so you are left with the central, nagging debate. Scientists still argue whether the lack of early fire evidence is a true signal of its absence or simply a problem of preservation. Are we missing the evidence because a million-year-old campfire is an incredibly fragile thing, a subtle arrangement of ash and charcoal easily erased by wind and rain? Or is the evidence missing because, for the first 1,000,000 years of their existence, they simply didn't have it? If they didn't, it makes their achievements, their migrations, their survival, their burgeoning intelligence all the more astonishing. They were conquering the world on hard mode. You are left with a profound paradox, a creature that seems to need fire to become itself, yet one that conquers the world long before it can be proven to have mastered a flame. This is the kind of puzzle that can stall a scientific story for decades. But what if we've been asking the wrong question? What if the choice wasn't just between raw food and roasted food? What if nature provided a third option, a clever workaround that gave our ancestors all the benefits of cooking without ever having to strike a spark? To find the answer, you have to go back to the heart of their world, to Olduvai Gorge, and look not at the bones, but at the very earth they walked upon. Recent groundbreaking scientific evidence has come from the geochemical analysis of ancient soil layers at Olduvai, dated to around 1.7 million years ago. What the analysis found were mineral deposits and chemical signatures consistent with one thing: hydrothermal features, geysers, fumaroles, hot springs. The ground beneath their feet was alive, bubbling and steaming with geothermally heated water. The mainstream historical fact is that the East African Rift is still one of the most geothermally active places on the planet, a landscape of volcanoes and hot springs. It was their environment, and it presents a stunning possibility. Imagine the scene. Instead of a crackling, smoky campfire, the center of your group's life is a series of turquoise pools veiled in a constant, warm mist. The air smells faintly of sulfur. After a hunt, you don't need to laboriously build a hearth. You simply take your cuts of meat, perhaps wrapped in leaves or hide, and place them in the bubbling, near-boiling water. You place tough, starchy tubers into the steam vents to soften. You are cooking. You are boiling, poaching, and steaming your food, using a source of heat that never goes out and requires no maintenance. This isn't just a fanciful image. It would have provided the exact same evolutionary advantages as fire-based cooking. The hot water would break down tough collagens in meat and soften plant fibers, making them easier to chew and digest. It would neutralize toxins and kill parasites. The quirky tidbit is that, from a nutritional standpoint, boiling is often a superior cooking method to high-temperature roasting, as it's less destructive to certain vitamins and nutrients. They would have been getting the maximum possible caloric bang for their buck, the perfect fuel for their expensive brains. It's an incredibly humanizing picture. You can't help but think of the famous Japanese snow monkeys, the macaques who spend their winters lounging in the natural hot springs of the mountains, grooming each other, dozing in the warm water, finding comfort and respite from the cold. Now, picture your Homo erectus ancestors doing the same. A small group, finished with their meal, relaxing in the warm, therapeutic waters, the children splashing at the edges. It's a scene not of brutal, relentless survival, but of intelligent, resourceful beings finding a pocket of paradise in a dangerous world. This hot tub time machine hypothesis is so compelling because it elegantly solves the chronological problem. It provides a mechanism for getting the metabolic benefits of cooked food right when Erectus needed it most, during the period of their most rapid brain expansion, 1.7 million years ago. It uncouples brain growth from the much later, much more difficult technology of controlling fire. It's a beautiful idea, but you have to remember its place in the scientific discourse. This is a relatively new and fringe idea, and many archaeologists still argue that pounding meat with stone tools to create a kind of paleo-tartare could have provided a similar digestive advantage without any heat at all. But as you watch the steam rise from those ancient pools, it's hard not to hope that this is how it happened. It's a story of our ancestors not as fearsome fire starters, but as clever hot tub chefs. Whether they were relaxing in a natural hot tub or simply resting after a long day's hunt, you begin to see that the most important part of their environment wasn't the landscape or the animals. It was each other. The old image of the brutish, club-wielding caveman, a lone wolf struggling against nature, is a complete fantasy. The entire evolutionary trajectory of Homo erectus was pushing them in the opposite direction, forcing them to become the most intensely social and cooperative primate the world had ever seen. Their very survival depended on it. Think about the three pillars of their new life. First, there's the hunt. You simply cannot take down a giant buffalo or a thick-skinned hippo by yourself. It requires a team, a group of individuals working together with a shared plan, communicating, and trusting one another to play their part. Second, you have those long, drawn-out childhoods, a direct consequence of being born with a smaller, underdeveloped brain that needed years to grow. This created a new class of beings within the group, helpless, demanding children who needed constant care, protection, and feeding for a decade or more. This is an incredible burden, one that would be impossible for a lone mother to manage while also providing for herself. And third, you have their technology. Making an Achulean Handaxe is a complex skill, a craft that has to be learned. This requires a teacher and a student, a system for transferring knowledge from one generation to the next. These three pressures, hunting, parenting, and teaching, all act like a powerful social glue, binding the group together. They would have almost certainly lived in larger, multi-generational bands than their Australopithecine ancestors, groups of maybe 20 to 30 individuals, a mix of experienced elders, prime hunters, caregivers, and a gaggle of curious, learning children. This is a complex social world, and its emotional depth is brought into stunning focus by that one fossil you keep coming back to. The toothless old man of Dmanisi. Let yourself picture him again. He is old, his face wrinkled, his body frail. He cannot chew. And yet, he is alive. Someone, perhaps his child, perhaps his mate, perhaps a younger hunter showing respect, is taking the time to prepare food for him. They are pounding meat into a paste, chewing roots to a soft pulp, or scooping out the rich marrow from a bone and feeding it to him. This is not the cold, brutish calculus of survival of the fittest. This is compassion. It is empathy. It is the recognition that an individual has value beyond their immediate physical utility. Perhaps he was a repository of knowledge, a living library of migration routes and tool-making tricks. Or perhaps they just loved him. This single act of care is a monumental leap into the realm of the truly human. Within this larger group, you would naturally see the emergence of a division of labor. This wasn't a formal org chart, but a fluid system based on skill, age, and circumstance. Some individuals, perhaps the younger males, might be the primary hunters. Others, perhaps women encumbered with children, would focus on gathering reliable resources like tubers, berries, and nuts, the foods that kept the group fed when the hunt failed. Another individual, a patient person with a good eye, might be the master flint napper, the one everyone came to for the best tools. This specialization makes the entire group more efficient and resilient. The mainstream historical fact is that this model holds true today. In modern hunter-gatherer societies, cooperation and the sharing of food and responsibilities are the absolute bedrock of their way of life. And all of this intricate social maneuvering required a new kind of intelligence. This is the core of the social brain hypothesis. The idea is that our brains didn't just get big to outsmart leopards or to map the landscape. They got big to outsmart, or more often, to cooperate with each other. A big brain is a social tool designed to navigate the fantastically complex world of other big brains. Who is my ally? Who is my rival? Who can I trust? Who owes me a favor? Keeping track of this social ledger, building coalitions, resolving disputes, and maintaining group cohesion is an immense computational challenge. The scientific evidence in the fossils backs this up. The reduced sexual dimorphism, meaning the smaller size difference between males and females in Homo erectus compared to earlier hominins, points towards a social structure with less male-on-male competition and more stable, cooperative partnerships. Even a feature as simple as the whites of our eyes, the quirky tidbit of our prominent sclera, is a powerful tool for social cooperation, allowing us to easily follow each other's gaze and understand what others are paying attention to. We are built to connect. But as with all things in this ancient past, the details remain a beautiful mystery. Anthropologists still argue about the specific kinship structures of Erectus societies, whether they were organized more like gorillas with a single dominant male, or more like chimpanzees in multi-male, multi-female groups with complex and shifting alliances. This new, intensely social world, with its complex web of cooperation and knowledge transfer, demanded a new tool, and this tool wouldn't be one of stone or bone, but one of breath and gesture. You cannot coordinate a hunt, teach a child to knap flint, or maintain complex social hierarchies with grunts and pointing alone. To make this new society work, you need language. And just like their bodies and their stone tools, language didn't just appear out of nowhere, fully formed. It had to have evolved, piece by piece, over an immense stretch of time. The very first building blocks, the foundational stones of every word you have ever spoken, were almost certainly laid down in the minds of Homo erectus. The clues are there, hiding in the architecture of their skulls. When you look at the endocasts, those ghostly impressions of the brain's surface, you see that the region known as Broca's area was already well developed. In modern humans, this area is critical for language production, for organizing thoughts into grammatical sentences. The fact that it was already taking shape in their brains 1.8 million years ago is a stunning clue. This neurological hardware wasn't developing in a vacuum. It was likely being driven by the immense cognitive demands of things like Achulean tool-making. The complex sequential process of crafting a Handaxe would have been fantastically difficult to teach without some form of demonstration, accompanied by, at the very least, a rudimentary system of communication. More recently, the story has moved from the shape of the bones to the code within our genes. Scientists have identified specific genes that played a huge role in the construction of the modern human brain. One of these, a gene with the catchy name SRGAP2C, has been described as a master switch. Its evolution, a kind of genetic stutter that duplicated an existing gene, appears to have happened right around the time Homo erectus emerged. In lab experiments, introducing this gene into mice caused their neurons to grow more complex branches and sprout more connections, essentially making their brains more densely wired and, presumably, smarter. It's a tantalizing piece of the puzzle, suggesting that a key genetic mutation provided Erectus with the upgraded neural hardware necessary for higher cognitive functions, including the first steps toward language. Now you must banish any image of them sitting around a campfire composing poetry. This wasn't Shakespeare. It was almost certainly a proto-language, a system far simpler than what we use today. Think of it as a collection of simple nouns: lion, water, rock, and verbs. Come, go, give. Perhaps linked together in short 2 or 3 word phrases. This vocal communication would have been richly supplemented with a whole vocabulary of hand gestures, body language, and facial expressions. But even this simple system would have been a revolutionary tool, allowing them to communicate with a clarity and precision that was impossible for their ancestors. The quirky tidbit in the genetic story of language is the famous FOXP2 gene, which is crucial for the fine motor control of the mouth and larynx that allows for articulate speech. While Homo erectus had an older, more primitive version of this gene, the key mutations that give modern humans their vocal dexterity and rapid-fire speaking ability likely appeared much later. This fits with the scientific evidence from the Turkana boy's skeleton. His thoracic vertebral canal, the channel in the spine that carries the nerves to the rib cage, is noticeably narrower than that of a modern human. This suggests he had less fine nerve control over his breathing, which would have limited his ability to produce the long, controlled exhalations needed for fluent, complex speech. He could talk, perhaps, but he couldn't give a lecture. This has led to one of the most enduring questions in linguistics. Scholars still argue whether language began as a vocal system that later incorporated gestures, or if it started as a sophisticated sign language that only later began to incorporate sounds. What is certain is that they were communicating, laying down the deep neurological structures that all human languages still rely on today. The mainstream historical fact is that all modern languages, from English to Mandarin, share fundamental underlying properties, a concept known as universal grammar, hinting at a single, deep origin for this incredible human ability. This new ability, this proto-language, was not an abstract parlor game. It was the single most effective survival tool they had ever developed. It was a weapon, a map, and a social contract all rolled into one. So what would you have talked about, standing there in the cool of the morning, the mists from the hot springs swirling around your knees? You would have talked about the things that mattered: food, water, safety, and each other. Imagine the hunt again. Without language, it's a chaotic, messy affair, relying on instinct and luck. But now, with a handful of shared sounds and gestures, it becomes a coordinated masterpiece of lethal strategy. The group leader doesn't just charge forward. He gathers the hunters. A low sound, maybe something like guro, points to the distant herd. A hand signal, a slicing motion across the body, indicates the target. A young, weak buffalo. Then the plan is communicated with a brutal simplicity. He points to 2 hunters and then points to his left. He points to 2 others and points to his right. You, left. You, right. A gesture of circling, of closing in. Everyone understands. The plan is set. As the chase unfolds, short, sharp barks of sound carry across the savannah, relaying information. Lion, far, or a gesture indicating the prey is tiring. This is the difference between a lucky meal and a full belly, between life and death. The applications would have permeated every aspect of your life. It was a tool for sharing vital information across time and space. A forager returns to the group and can now communicate more than just a general direction. They can say, "Water, there," pointing, and then, holding up a piece of honeycomb, "Sweet thing, there too." This is a revolution. Knowledge is no longer locked inside a single individual's head, doomed to die with them. It can be shared, pooled, and passed on. A child sits at the feet of a master flint knapper who, instead of just letting the apprentice learn by imitation, can now guide their hands and say, in a string of simple commands, "Rock, bad, hit, here, softer." And of course, you would have talked about each other. Language is the ultimate tool for navigating the complex, soap-operatic world of social relationships. You could now express approval or displeasure, warn someone who was violating a social rule, or build an alliance with a trusted friend. You could gossip. It sounds trivial, but gossip is a powerful social tool for monitoring reputations and enforcing group norms. And as the sun went down, you would have used words to do something truly magical. Tell stories. The mainstream historical fact is that storytelling is a universal human trait, a foundational technology for transmitting a group's history, its values, and its collective wisdom. Perhaps you would recount the day's hunt, embellishing your own bravery. Or maybe an elder would tell a story about a mythical ancestor who outsmarted a saber-toothed cat. The quirky tidbit is that some linguists propose that the very first words were onomatopoeic, direct imitations of the sounds of the world. The word for lion might have been a low, rumbling growl. The word for a bird might have been a tweet or a caw. The word for a striking snake, a sharp hiss. It's a compelling idea. That language began by simply mirroring the sounds of nature. The scientific evidence, however, suggests their speech would have sounded very different from ours. The position of the larynx, or voice box in Homo erectus, was likely higher in the throat, similar to that of a human baby or a chimpanzee. This would have severely restricted the range of vowel sounds they could produce. Their speech would have lacked the melodic subtlety of ours, being more guttural and less nuanced, yet no less effective for their purposes. This all leads to a fundamental debate. Linguists still argue whether language evolved primarily for social bonding, for grooming our relationships, gossiping and telling stories, or for practical information exchange about the environment and technology. Was it a tool for the heart or a tool for the hand? The truth is, it was almost certainly both. It was the master tool that allowed for the accumulation of knowledge over generations. For the first time, a creature on Earth could build a library of shared wisdom. This is the birth of culture, a new kind of evolution that works on the time scale of stories and ideas, not the slow, grinding pace of genetic change. And Homo erectus was its first author. Your new language, this web of shared ideas, gives you a power that is far more potent than any sharp stone. The power of culture. And it is this power that allows your species not just to survive, but to thrive for an almost unimaginable stretch of time. You must now shift your focus away from Africa, the cradle, and travel east across thousands of miles and hundreds of thousands of years. You arrive in Southeast Asia, a world of tropical woodlands and volcanic islands. Here, Homo erectus established a dynasty. They lived in this part of the world for well over 1 million years, adapting to its unique rhythms, its unique animals, and its unique challenges. For context, that is a reign 4 times longer than our own species has yet managed. They were the undisputed, long-reigning kings of prehistoric Asia. And for a long time, we thought we understood how they got there. During the peaks of the ice ages, so much of the world's water was locked up in massive continental glaciers that sea levels were hundreds of feet lower than they are today. This exposed vast stretches of the continental shelf, connecting lands that are now separated by sea. The islands of Java, Sumatra, and Borneo were not islands at all. They were all joined to the Asian mainland in a single continuous landmass known as Sunda. It was a simple story. Homo erectus simply walked there, following the expanding grasslands and the herds of animals, just as they had walked out of Africa. Then, on the island of Luzon in the Philippines, a discovery was made that tore this simple story to shreds. Archaeologists found a 700,000-year-old butchered rhinoceros skeleton. Its ribs were smashed. Its limbs bore the unmistakable cut marks of stone tools, and the stone tools themselves were lying right there beside it. The evidence was irrefutable. A hominin had been on Luzon, feasting on a rhino 750,000 years ago. And that presents an enormous problem. Because Luzon, like the nearby island of Flores, was never, ever connected to the Sunda landmass. The geological and biological story of this region is defined by a deep, invisible line in the ocean. The mainstream historical fact is the existence of the Wallace Line, a deep oceanic trench that separates the fauna of Asia from that of Australia. It is an ancient and profound barrier. Even at the lowest sea levels of the Ice Age, This trench remained a wide, deep water channel, a permanent moat that land animals could not cross. The scientific evidence from geological surveys confirms this unequivocally. To get to islands like Luzon or Flores, you had to cross at least a few miles of open, unpredictable sea. There was no land bridge. There was no way to walk. The conclusion is as inescapable as it is astonishing. They must have crossed the water. This single fact forces a complete re-evaluation of their capabilities. We see them as terrestrial, savanna-adapted walkers. But here is proof that their world and their ingenuity extended to the sea. The quirky tidbit that puts this in perspective is thinking about the incredible, sophisticated maritime cultures that would arise in the same region tens of thousands of years later. Ancient Polynesian mariners would navigate thousands of miles of open ocean using nothing but the stars, the wave patterns, and the flight of birds. A body of knowledge built over countless generations. The Homo erectus crossing would have been infinitely more rudimentary, an act of either breathtaking courage or unbelievable luck. They had no maps, no sails, no navigational science. They only had the sight of an island on the horizon and some unknown means of getting there. This discovery opens up one of the most exciting and fiercely contested questions in modern paleoanthropology. This is one of the hottest debates. Were these sea crossings a deliberate, intentional act of exploration, or were they the result of a terrifying, accidental rafting event? Did a small group see that distant, hazy coastline, build some kind of simple watercraft, and bravely paddle into the unknown? Or was a family group simply caught on the coast during a massive tsunami, swept out to sea on a floating mat of tangled vegetation, and by a 1 in a billion chance washed ashore alive on a new island? The answer to that question changes everything. So you are standing on the edge of a prehistoric beach, the humid Southeast Asian air thick and heavy around you. In the distance, across a stretch of shimmering, unpredictable water, a hazy purple shape smudges the horizon. An island, a new world. What happens next inside your Homo erectus mind? This is the heart of the mystery. Do you see that water as an absolute, impassable barrier, the end of your world? Or do you see it as a challenge, a pathway to something new? The answer to that question splits into two vastly different stories. The first is the story of the accidental sailor. In this version, you are not a pioneer, you are a victim. Imagine a day that starts like any other, foraging along the coast. Suddenly, the sea pulls back, a strange and terrifying emptiness exposing the seabed for hundreds of yards. The birds fall silent. Then you hear it, a low, distant roar that grows into a world-ending cataclysm. A tsunami. A wall of water obliterates the coastline, and your entire world is torn apart. By a 1 in a billion chance, you and a few members of your family group find yourselves clinging to a massive, buoyant raft of uprooted trees, soil, and tangled vegetation, a floating island of chaos swept out into the open ocean. You are now adrift, helpless. The days that follow are a blur of terror, thirst, and sunstroke. Sharks circle. You have no food, no fresh water. One by one, your companions weaken and die. But your luck, your impossible, absurd luck, holds. Before you succumb, the currents wash your natural raft ashore on the beach of that new island. You stumble onto the sand, alone or with a single other survivor, the sole, accidental Adam or Eve of a new hominin world. This scenario requires no intelligence, no foresight, no courage. It requires only luck of the most astronomical kind. It's the ultimate lottery ticket theory of prehistoric colonization. And while it is certainly possible for a single event like this to happen, you must ask yourself, is it a plausible explanation for a stable, breeding population to establish itself? Could it happen twice to explain the separate island populations in the Philippines and on Flores? Now, consider the second story, the story of the intentional sailor. In this version, you are not a victim, you are an agent. You have seen that hazy purple island on the horizon for your entire life. You have watched the smoke from distant natural volcanoes rise from it. You understand that it is a real place, and your world here is becoming crowded. The herds are getting thinner, or perhaps a rival group has pushed you from your territory. That island is not just a shape, it is a promise. It's a place with no rivals, a place of untapped resources. The water is not an absolute barrier. It is simply a problem to be solved. So, you begin to work. The mainstream historical fact is that this region is, and was, a world of bamboo. Giant, thick-walled bamboo, incredibly strong and filled with pockets of air, making it naturally buoyant. You and your group, using your simple stone choppers, begin to harvest it. The air fills with the rhythmic, percussive sound of stone striking wood. You lash the poles together with strong, flexible vines. You are building something that has never existed before, a watercraft. The quirky tidbit is that modern experiments have repeatedly shown that a small group of people, using only the kinds of stone tools available to Homo erectus, can build a perfectly functional and stable bamboo raft in just a matter of days. It is entirely within their technological reach. And so, on a calm morning, you and your small band of adventurers push your clumsy, ugly, beautiful craft into the surf and begin to paddle with your hands, your eyes fixed on that distant promise. This scenario requires no luck at all. It requires something far more profound. Foresight, planning, cooperation, and a level of abstract thought that is simply staggering. It's the ability to look at a solid thing, bamboo, and a liquid thing, water, and understand that one can be made to travel over the other. It's the courage to leave the known world behind and paddle into a blue, terrifying unknown. The scientific evidence that lends weight to this idea is the very existence of multiple, distinct island hominin species. Homo floresiensis on Flores and Homo luzonensis in the Philippines. A 1 in a billion accidental event is a statistical anomaly. 2 or more such events in the same region begins to look like a pattern. It suggests that getting from island to island was something they knew how to do, even if it was incredibly risky. Of course, the debate rages on. Archaeologists still argue that without the discovery of an actual Homo erectus boat, the intentional crossing hypothesis remains pure speculation. We have no fossilized rafts, but whether they were brilliant accidental survivors or clumsy, courageous mariners, the result is the same. They broke the bonds of their terrestrial world. They looked at the sea, a barrier that had contained every land animal for millions of years, and they crossed it. For a creature to possess the abstract thought necessary for sea travel is one thing, but how do you find concrete proof of that inner world? How do you find a fossil not of a bone, but of an idea? For decades, the answer was, you don't. The world of Homo erectus was seen as a purely functional one, a world of stone tools and butchered animals, utterly devoid of the art, symbolism, and ritual that we associate with the human soul. And then a Dutch researcher, looking through a dusty, forgotten collection of artifacts in a museum drawer, found something that would rewrite the very definition of who these ancient people were. The object itself is humble. It's a freshwater mussel shell, dark and unassuming, of the species Pseudodon. It was originally unearthed in the 1890s at a site called Trinil on the island of Java, Indonesia, from layers of earth firmly dated to between 400,000 and 500,000 years ago. This places it squarely in the time of Homo erectus, hundreds of thousands of years before Homo sapiens would even exist. The quirky tidbit that adds a touch of historical poetry is that this shell was found at the very same site, Trinil, where the Dutch physician Eugène Dubois discovered the very first Homo erectus fossil, the famous Java man, launching the entire scientific search for human origins. For over a century, this shell and hundreds like it sat in a museum collection in the Netherlands. The mainstream historical fact is that these artifacts were part of Dubois' original collection, but they were considered little more than paleontological curiosities, the fossilized remains of ancient meals. No one looked at them closely, but in 2014, a researcher named Josephine Jordans did. And as she tilted one particular shell under the light, she saw it. Scratched onto its surface was a deliberate geometric zigzag pattern. It was an M-shaped series of lines, connected in a crisp, confident engraving. The immediate question, of course, was whether this was intentional. Could it have been an accident, the random scratching of an animal's tooth, or the result of some natural geological process? The scientific team that assembled to study the shell was meticulous. They put it under powerful microscopes and created high-resolution digital models. The scientific evidence was conclusive. The analysis showed that the grooves were made with a single sharp tool, something like a shark's tooth, which was also found in the same geological layer. The strokes were smooth, confident, and continuous, made with a steady hand. Critically, the analysis also showed that the engraving was made when the shell was fresh. The tool was cutting through the living organic matrix of the shell, not brittle, fossilized calcite. This was not a random doodle. This was not an accident. This was a deliberate act, a design executed with precision and purpose. Let that sink in. 500,000 years ago, a Homo erectus sat on the bank of a river in Java. They collected these shells, likely for food. But with one of them, they did something more. They picked up a tool, and with a focused mind and a steady hand, they carved a symbol. A pattern that exists nowhere in nature. It is arguably the single oldest piece of art in the world. It is a message in a bottle, a whisper from a mind that we had long assumed was silent and dark. It is a geometric thought, preserved for 500,000 years. This simple zigzag throws all our assumptions into the air. But what did it mean? That is the question that echoes from that ancient riverbank. The key debate is, naturally, about its meaning. Is it symbolic art in the way we understand it? Is it a simple ownership mark, a way of saying, this shell is mine? Or is it simply the result of an idle, focused action with no deeper meaning, the prehistoric equivalent of a bored student doodling in the margins of a notebook? We will never know for sure, but the act itself is what matters. You try to decipher the meaning of this ancient mark, but it's a language with only one known word. Was it a map? A story? A symbol for water or a god we can't imagine? The truth is, we will never know. And in a way, its specific meaning doesn't matter. The revolutionary act was not in the message, but in the creation of a message in the first place. The act of making the pattern is itself symbolic. It is taking an abstract, geometric idea from inside your mind and imposing it upon the world. It's the ability to make something that represents more than just itself. It's the understanding that a mark can mean something. This is the spark. From this one, humble zigzag, a direct, unbroken line of human creativity can be drawn. This is the seed from which all later art will grow. It is the same impulse that will, 450,000 years later, lead your Homo sapiens descendants to mix ochre and spit and spray the outlines of their hands on a cave wall in Sulawesi. It is the same spark that will drive the creation of the Venus of Willendorf, the paintings of the Lascaux caves, the pyramids of Giza, and the cathedrals of Europe. It all begins here, with a bored or inspired hominin, a shark's tooth, and a mussel shell on the bank of a Javanese river. You must then consider the overwhelming probability that this was not a unique, isolated act. Think of all the art you have ever created in your life that has simply disappeared. The drawings you made in the sand at the beach, washed away by the tide. The figures you carved into the bark of a tree that has long since rotted away. The patterns you painted on your own skin with charcoal or clay. Art made on perishable materials is the vast, invisible library of human history. For every one stone tool that has survived, how many beautifully carved wooden spears have turned to dust? For this one engraved shell, how many millions of similar marks were made on hides, on bark, on the surface of the earth, or in patterns of flowers and feathers, all lost to the ages? The shell is not the first piece of art. It is simply the first piece of art that was lucky enough to be made on a material that could outlast 500,000 years of geology. This brings us back to that central, defining question of your journey. Are these creatures truly human? If the capacity for symbolic expression is one of the profound markers of humanity, then this shell is a closing argument. Here, in this simple zigzag, you see the unmistakable flicker of a modern mind. You can even see a hint of the artist's process in the scientific evidence. The location of the engraving on the shell is near the muscle attachment point, precisely where it would have been most visible and stable if you were holding the shell in your left hand and carving it with your right. You can almost feel the quiet, focused moment of its creation. The mainstream historical fact is that the oldest, most undeniable evidence for the creation of pigments, red ochre processing kits, dates back to about 100,000 years ago in Blombos Cave, South Africa, and is clearly associated with our own species. We were a colorful people from early on, but the evidence for Erectus using ochre is more ambiguous. They may have used it, but this shell is the only clear proof of their symbolic production. A fascinating and quirky tidbit comes from neuroscience. Some researchers have pointed out that simple geometric patterns like zigzags and chevrons are common phosphenes, the shapes your brain generates internally and that you see when you close your eyes and press gently on your eyelids or in altered states of consciousness. It's a mind-bending possibility that the first art wasn't an imitation of the outside world, but a depiction of the internal, neurological world of the artist. But even with this stunning piece of evidence in hand, a debate continues. Scholars still argue whether this shell represents a species-wide cognitive ability, a sign that all Homo erectus were capable of this kind of thought, or if it was the unique act of a single, genius Homo erectus individual, a prehistoric Leonardo da Vinci who was a cognitive anomaly far ahead of their time. Was this the norm, or a brilliant, lonely exception? We may never know, but the fact that it happened at all changes the story forever. That creative spark, that first flicker of symbolism on a Javanese shell, was not a brief flash in the pan. It was a single moment in the longest, most successful story of any human species that has ever lived. You have to recalibrate your entire sense of time to appreciate the reign of Homo erectus. Our own species, Homo sapiens, with all our cities, our technologies, and our moon landings, has been around for about 300,000 years. Our famous cousins, the Neanderthals, with their mastery of Ice Age Europe, lasted for about 400,000 years. These are impressive runs by any measure, but Homo erectus looks at those numbers and scoffs. They existed as a recognizable, cohesive species for nearly 2 million years. From their first appearance in Africa around 1.9 million years ago to their final stand on a riverbank in Indonesia, they endured. They are not just a chapter in the human story. For an immense stretch of time, they were the human story. Their astonishing success was built on a foundation of stability. They had figured out a formula that worked, and they saw no reason to change it. That Achulean Handaxe, that perfect, symmetrical, all-purpose tool, remained their signature piece of technology, almost completely unchanged for over 1 million years. Imagine using the same model of iPhone for 1 million years. It's a level of cultural conservatism that is almost impossible for our novelty-obsessed minds to comprehend. They had achieved a perfect equilibrium with their world. They were adaptable enough to spread across 3 continents, from the heat of the African savanna to the temperate woodlands of Asia. But their core toolkit, their fundamental way of being, remained the same. They were the ultimate survivors, the steadfast, enduring trunk of the human family tree. But this incredible stability, their greatest strength, may have also been their fatal flaw. The world does not stand still. While Erectus was perfecting its million-year-old formula, evolution was busy in the background, tinkering with new models. In Africa and Europe, new, even bigger-brained hominins were emerging from their lineage. Creatures like Homo heidelbergensis, who would in turn give rise to the Neanderthals and to us. These new humans were different. They were innovators. Their toolkits were more varied, more adaptable, changing rapidly to suit local conditions. They were specialists, not generalists. Homo erectus was the old, established global empire, and these new species were the nimble, fast-adapting upstarts emerging at the fringes. For hundreds of thousands of years, they all shared the planet. But the long, slow goodbye for Homo erectus seems to have happened in the east, in their ancient heartland of Southeast Asia. The mainstream historical fact, established by recent dating techniques, is that the very last known population of Homo erectus survived at a site called Ngandong on the Solo River in Java, until as recently as 117,000 years ago. This date is shocking. It's practically yesterday in geological time. This leads to a mind-bending, quirky tidbit. It means that when the first bands of fully modern Homo sapiens, your direct ancestors, were beginning their great migration out of Africa, a relic population of their immensely ancient forebears, Homo erectus, was still alive and well on an island in Indonesia. For a time, the world was shared. It was a world of ancient, grizzled elders and fresh-faced newcomers. A planet that contained both the very dawn and the modern noon of humanity at the same instant. The scientific evidence from the animal fossils found alongside these last Erectus at Ngandong tells us exactly what their world was like. It was a familiar, open woodland environment, filled with the kinds of deer and ancient cattle they had been successfully hunting for 1,000,000 years. They were in their comfort zone, the last bastion of a world that was rapidly changing around them. And this brings us to the final, great mystery of their story. The cause of their final extinction is heavily debated. Did they meet us? Was their final disappearance the result of a direct competition with the new, clever, fully modern humans who were sweeping across Asia? Or were they simply a casualty of a much larger, more impersonal force, the planet's ever-changing climate? You focus your attention on that last outpost of an ancient race, on that riverbank in Ngandong 117,000 years ago. You are watching the final act of a 2,000,000-year epic. It wasn't a dramatic, bloody battle against a new, smarter human that ended their story. It was something quieter, slower, and far more inexorable. The world that had sustained them for 1,000,000 years in this part of the globe simply vanished from beneath their feet. The culprit was climate change. The mainstream historical fact is that the entire planet was in a state of flux during this period, approaching the great transition from the Pleistocene epoch to our own warmer, wetter Holocene. The gears of the global climate were shifting, and for the last Homo erectus of Java, that shift was a death sentence. Their entire evolutionary toolkit was designed for a specific kind of world, the open woodland and savanna, a park-like landscape with patches of forest interspersed with vast grasslands, roamed by large herds of grazing animals. Their bodies, their tools, their hunting strategies, everything was perfectly tuned to this environment. But now, as the climate warmed and rainfall increased, that world began to dissolve. The grasslands started to shrink. The trees grew closer together, their canopies interlocking, creating a dense, humid, closed-in world. The open woodland was suffocating, transforming into a true tropical rainforest. This new environment was a biological prison for you. First, and most simply, your food disappeared. The large herd-dwelling grazers like the ancient cattle and deer you had hunted for millennia couldn't survive in the dense forest undergrowth. They retreated or died out, replaced by more solitary, nimble, forest-adapted creatures. Your entire economic system, built on the predictable movements of big game, collapsed. Second, your greatest physical advantage, your superpower, was rendered useless. The ability to run for hours under an open sky is a devastating weapon on the savanna. In a dense, tangled jungle, full of trip hazards, thick vegetation, and limited lines of sight, it is utterly worthless. Your primary hunting strategy was obsolete. Third, and perhaps most critically, your own body, that masterpiece of tropical engineering, began to work against you. Your tall, linear frame was designed to dissipate heat efficiently in a dry climate. But in the suffocating, near 100% humidity of a rainforest, sweating no longer works. The moisture can't evaporate from your skin, so it provides no cooling. Instead of shedding heat, you are now trapping it, constantly at risk of overheating with any strenuous activity. The very air feels heavy and wet, a physical burden. This new, lush world was, for your physiology, a sweltering green hell. The quirky tidbit that ecologists understand well is that a tropical rainforest, for all its vibrant life, can be a green desert for large terrestrial animals like you. Most of the energy and biomass is locked up high in the canopy or in inedible wood, leaving the forest floor surprisingly poor in accessible calories. You can feel the slow, inevitable tightening of the evolutionary vice. Your food is gone, your best hunting trick is useless, and your own body is failing you in the oppressive heat and humidity. The scientific evidence for this environmental change is not speculative. It's written in the earth at the Ngandong site itself. Pollen and soil analysis from the fossil layers tells a clear story, showing a definitive transition from the pollens of a cooler, drier woodland environment to those of a warmer, wetter, and much denser rainforest ecosystem. They were trapped. Their million years of stability, of perfecting a single successful way of life, had turned them into specialists of a world that no longer existed. They couldn't adapt quickly enough. They were a relic, a living fossil from another time, and their time was finally, after 2 million years, running out. So you stand by the banks of the Solo River and watch the last of them. A small, dwindling band, perhaps struggling with new diseases found in the damp forest, finding it harder and harder to find food. Their children weaker, their future as closed in as the canopy above their heads. They didn't fall in a great war. They just faded away, their ancient lineage finally extinguished by the inexorable, indifferent shifting of the wind and the rain. And of course, the story may be more complex. Scientists still argue whether other factors, like the arrival of new, specialized forest predators or novel diseases to which they had no immunity, may have played a contributing role in their demise alongside the overwhelming pressure of climate change. But the verdict remains the same. The longest story in human history had come to a quiet, damp, and lonely end. But the end of the main line of Homo erectus in Java was not the end of their story. Their 2-million-year journey across the globe had left behind seeds, small, isolated populations scattered on islands and in hidden valleys. In these isolated laboratories of evolution, their lineage would continue to twist and change in the most unexpected ways. The ghost of Homo erectus would linger, leaving behind children so strange they would force us to redraw the human family tree. The first and most famous of these lost children was found in 2003 in a cool limestone cave called Liang Bua on the Indonesian island of Flores. The discovery was a bombshell. The team of archaeologists unearthed the partial skeleton of an adult female hominin. But she was unlike anything they had ever seen. She was tiny, standing only about 3.5 feet, 1.1 meters, tall. Her feet were clownishly large for her short legs, and her head was shockingly small. A reconstruction of her skull revealed a brain volume of just over 400 cubic centimeters. This is not just small by human standards. It's the size of a modern chimpanzee's brain. And yet, found all around her in the cave were stone tools that were surprisingly sophisticated. Tools that showed a level of skill and planning consistent with the much larger-brained hominins of the mainland. As the team dated the skeleton, the mystery only deepened. She had lived and died just 50,000 years ago. This was not some ancient, primitive ancestor from millions of years in the past. This tiny, small-brained human was a contemporary of fully modern Homo sapiens. While your ancestors were painting masterpieces on cave walls in Europe and migrating across Australia, this strange creature was living and hunting in the forests of Flores. The scientific world was stunned. They nicknamed her the Hobbit, after the small folk of Tolkien's novels. The first skeleton found was officially catalogued as LB1, but the mainstream historical fact is that she is almost universally known by her affectionate nickname, Flo. What on earth was she? The leading theory is that Homo floresiensis, as the new species was named, is a direct descendant of Homo erectus. The idea is that a population of standard, full-sized Homo erectus managed to cross the water barrier to Flores hundreds of thousands of years earlier. Once stranded on this isolated island, they were subject to a powerful and bizarre evolutionary pressure known as insular dwarfism. It's a well-known phenomenon in evolutionary biology. On islands with limited resources and fewer predators, large animals tend to shrink over many generations. Flores itself provides the perfect context. Fossils of a pygmy version of an ancient elephant-like creature, the stegodon, have been found all over the island. The theory is that the hominins simply followed the same evolutionary path, their bodies and, most controversially, their brains shrinking in response to the island's unique ecological pressures. This idea is a testament to the incredible, almost unbelievable adaptive potential of the Erectus lineage. It suggests their brain, while it shrank in size, must have reorganized itself to become incredibly efficient, retaining the software for complex thought and tool-making while running on much smaller, more energy-efficient hardware. The story is made all the more tantalizing by the local folklore of the island. The quirky tidbit that sends a shiver down the spine is that the oral traditions of the people living near Liangbua Cave tell of small, hairy, human-like creatures they called the Ibu Gogo, or the grandmother who eats anything. The legends say they were fast runners, they murmured in their own language, and that they were still present on the island when the first Dutch trading ships arrived a few centuries ago. Is it possible that these are the last, fading folk memories of a real, non-sapiens human who shared their world? Of course, a discovery this radical was bound to be controversial. A minority of scientists still argue that Floresiensis isn't a separate species at all, but rather a population of modern humans that suffered from some kind of pathological condition like microcephaly or a severe iodine deficiency leading to cretinism. The scientific evidence, however, pushes back hard against this. Analysis of the Hobbit's wrist and foot bones shows a strange mosaic of features. Some are advanced, like those of Homo, but others are remarkably primitive, more closely resembling those of a 3-million-year-old Australopithecus. This unique combination of traits is not seen in any known human pathology, suggesting they are a genuine, distinct, and very, very strange branch of the human family. The child of Erectus had become something new, a creature that challenges our very definition of what it means to be human. If the Hobbit of Flores was a strange, shrunken child of the Erectus lineage, then another discovery, back in the African homeland, would reveal a ghost from a completely different part of the family. A creature so enigmatic, it feels less like a fossil and more like a riddle sent from the past. The story begins in 2013, deep within a labyrinthine network of limestone caves near Johannesburg, South Africa, known as the Rising Star Cave System. Two local cavers, squeezing through a passage so tight it was called Superman's Crawl, discovered a hidden chamber, its floor littered with a breathtaking carpet of bones. What they had found was not just a new fossil. It was a treasure trove, one of the most significant hominin discoveries of all time. What emerged from that chamber was a new species, named Homo naledi, and the sheer quantity of fossils was staggering. Over 1,500 individual bones and teeth, belonging to at least 15 distinct individuals, from infants to the elderly. It was an entire population, a fossilized community, and they were a baffling mosaic of ancient and modern. If the Hobbit was a strange but somewhat predictable result of island evolution, Naledi was a creature that seemed to defy all the rules. Their brains were tiny, averaging just over 500 cubic centimeters, not much bigger than the Hobbit's and well within the range of an Australopithecine. Their shoulders were shaped for climbing, and their fingers were long and curved, perfect for gripping branches. These were primitive, ancient traits, but from the waist down, they were shockingly modern. Their legs were long and slender, and their feet were virtually indistinguishable from your own, built for efficient, long-distance walking. They were a bizarre chimera, an ape-like climber from the waist up, and a modern human-like strider from the waist down, all topped with a brain the size of an orange. But the biggest shock of all was their age. Given their primitive features, everyone assumed they must be ancient, a relic from the very dawn of the genus Homo, perhaps 2 million years old. The dating results, when they finally came, were an explosion. Homo naledi lived between 335,000 and 236,000 years ago. This is not the distant past. It is our own backyard. They were alive in Africa at the exact same time that the first large-brained early Homo sapiens were emerging. A small-brained, primitive-looking ghost from our deep past was sharing the landscape with our own direct ancestors. Their precise ancestry is still a puzzle, but their modern-looking legs and feet strongly suggest they are not a holdover from the Australopithecines. The most likely scenario is that they are another isolated, long-surviving offshoot of the Homo erectus lineage, a branch that split off early and evolved down its own strange path for 1 million years, retaining some primitive traits, while independently evolving others that look remarkably modern. Their name, the quirky tidbit in this story, is a nod to their place of discovery. In the local Sotho language, Naledi means star, a beautiful tribute to the rising star cave. But their anatomy is not the biggest mystery. The real riddle is how they got there. The Dinaledi chamber, where they were found, is almost 1,000 feet from the cave entrance, through a series of incredibly tight, dangerous passages. The final chute into the chamber is a vertical drop just 7 inches wide. This was not a pleasant place to live. It is a pitch-black, inaccessible death trap. So how did 15 individuals end up there? The chamber shows no signs of a predator dragging them in, and there is no evidence of a flood that could have washed them in from the surface. This has led Lee Berger, the paleoanthropologist who led the discovery team, to a conclusion that is as profound as it is controversial. They were put there deliberately. He argues that Homo naledi, this small-brained creature, was intentionally disposing of its dead, carrying them through the terrifying darkness to this deep chamber, a behavior we once thought was unique to big-brained modern humans. The mainstream historical fact of the discovery itself is a story of modern exploration. To retrieve the fragile bones, the team had to recruit a special crew of 6 small female paleoanthropologists and cavers who were nicknamed the Underground Astronauts. They were the only ones slender enough to repeatedly fit through the perilous 7-inch slot. The very latest scientific evidence from the cave system has added even more fuel to the fire. In adjacent chambers, the team has recently reported finding evidence of hearths containing charcoal and burned animal bones, and even a series of crosshatch engravings on the cave walls, all attributed to Naledi. The implication is mind-shattering. A hominin with a brain 1/3 the size of ours may have not only controlled fire, but created art, and practiced a form of ritualistic burial. Of course, this is where the scientific battle lines are drawn. The idea of intentional body disposal by Naledi is fiercely contested. Many other archaeologists argue that the bodies could have washed into the cave from a different, now collapsed entrance, or that a predator could have used the cave as a den, or that individuals simply got lost and died there over a long period. To them, the claim of complex symbolic behavior in such a small-brained creature is an extraordinary one that requires far more evidence. But whatever the answer, Homo naledi is a ghost that haunts us, a creature that breaks all the rules and forces us to ask whether brain size is really the only measure of what it means to be human. You've seen the strange children of the Erectus lineage, the Hobbit and Naledi, evolutionary side quests that ultimately led nowhere. But what about the main story? What about the direct line that leads from a million-year-old Homo erectus to you? You look for a neat, clean, father-to-son succession in the fossil record, but instead, you find a frustrating gap. The trail goes cold. You have entered a period of paleontological fog, a confusing and poorly understood era between about 800,000 and 500,000 years ago that scientists have affectionately and accurately nicknamed the Muddle in the Middle. The fossil record from this period is sparse, fragmented, and maddeningly ambiguous. The skulls and bones you find are a confusing jumble of features. Some look like advanced, big-brained Homo erectus. Others look like primitive early Neanderthals. And some look like a bit of both. It's an evolutionary transition caught in the act, and untangling who is who and who is related to whom is one of the toughest jobs in all of paleoanthropology. Out of this muddle, however, one candidate has emerged as the most likely bridge between the ancient and the modern. This new character on the stage is called Homo heidelbergensis. They were tall, powerful hunters, with brains that were now well within the modern human range, averaging over 1,200 cubic centimeters. They had the massive brow ridge of their Erectus ancestors, but their faces were flatter, and their brain cases were higher and more rounded. They were the perfect intermediate form, a creature standing with one foot in the world of Erectus and the other in the world that would produce us. The leading theory, the one that makes the most sense of the available evidence, places heidelbergensis at a crucial fork in the human road. The story goes like this. Back in Africa, a population of Homo erectus, or ergaster if you prefer, continued to evolve, growing larger bodies and bigger brains, eventually becoming Homo heidelbergensis. For a time, they thrived in their homeland. Then, perhaps around 600,000 years ago, a group of them staged a second great out-of-Africa migration. One branch of these pioneers pushed into Europe and Western Asia. Over the next few 100,000 years, isolated by distance and adapting to the colder climates of the Ice Age, they would evolve into the Neanderthals. Another branch pushed into Eastern Asia and became the mysterious Denisovans. And what of the population of heidelbergensis that stayed behind in Africa? They too continued to evolve, their faces shrinking, their chins emerging, their skulls becoming even more globular. They would eventually become us, Homo sapiens. This narrative makes Homo heidelbergensis the crucial link, the last common ancestor that we share with our famous, long-lost cousins. The mainstream historical fact is that the species gets its name from the Mauer jaw, a massive and robust mandible discovered in a sand quarry near Heidelberg, Germany, way back in 1907. The most incredible evidence for the sophisticated, and perhaps even spiritual, lives of these ancestors comes from a site in northern Spain called Atapuerca. There, deep inside a cave system, is a vertical shaft known as the Cima de los Huesos, the Pit of Bones. It's a chilling and poignant place. At the bottom of this shaft, archaeologists have found the commingled remains of at least 28 heidelbergensis individuals, men, women, and children. This was not a place where they lived. It seems to have been a place where they were deliberately dropped, one by one, after death. Among the jumble of bones, a single beautifully made handaxe of striking red quartzite was found, the only tool in the entire pit. This incredible quirky tidbit has been nicknamed Excalibur, and it's been interpreted as a kind of grave offering, a final ritualistic tribute to the dead. It is perhaps the world's first burial. The scientific evidence from this incredible site has become even more powerful in recent years. Scientists have managed to extract ancient DNA from the Sema fossils, and it has confirmed their place in the family tree. They are the genetic ancestors of the Neanderthals. The muddle is beginning to clear, but as always, not everyone agrees. Some paleoanthropologists reject the heidelbergensis category entirely, calling it a wastebasket taxon. A convenient but unscientific label where any confusing fossil from this time period is dumped. They argue for a more direct, continuous line of evolution from Erectus to the later human forms, without the need for this intermediate species. The debate continues, but the picture of a common ancestor, a great human trunk from which the three big branches of recent humanity, sapiens, Neanderthals, and Denisovans, would sprout, is coming into sharper and sharper focus. This new, clearer picture of Homo heidelbergensis as the common ancestor seems to solve the puzzle. It gives you a neat branching tree. But for decades, this out-of-Africa model had a powerful and persistent rival, a completely different way of looking at the human story. To its proponents, the idea that one small group of Africans simply replaced every other human on the planet felt too simple, too clean. This alternative idea was called the multi-regional hypothesis, and it painted a picture of humanity that was not a branching tree, but a single, sprawling, interconnected web. In this version of the story, the great out-of-Africa migration of Homo erectus over 1 million years ago was the only one that really mattered. After they had spread across the 3 continents, they didn't evolve in isolation. Instead, this entire globe-spanning network of archaic humans evolved together into Homo sapiens. The populations in China, Indonesia, Europe, and Africa were all on the same slow-moving evolutionary train, kept on the same track by a constant trickle of gene flow, interbreeding between neighboring groups that passed new traits back and forth across the network, like ripples in a pond. The mainstream historical fact is that this idea was most famously and forcefully championed by the paleoanthropologist Milford Wolpoff, who argued it was the best way to explain why certain anatomical traits seemed to persist in specific regions for hundreds of thousands of years. For a long time, it was a legitimate and heated debate, fought with skulls and stones as the primary evidence. Then, in the late 1980s, a new kind of evidence emerged that would act like a nuclear bomb on the multi-regional hypothesis: genetics. By studying the mitochondrial DNA of people from all over the world, scientists were able to build a human family tree based on the actual code of life. And the result was an unambiguous thunderclap. The scientific evidence was overwhelming. The genetic diversity of modern African populations is greater than that of the rest of the world combined. This is the classic signature of a population bottleneck, or a founder effect. It means that a small group from a large, diverse parent population, Africans, left their homeland and populated the rest of the globe. All non-Africans are the descendants of this small band of pioneers. Genetically, we are all recent Africans. The multi-regional model, in its classic form, was dead. The evidence for a recent African origin was simply too strong to ignore. The replacement model had won. But then, as our ability to read ancient DNA became more and more sophisticated, the story took one last spectacular twist. When scientists finally sequenced the genome of a Neanderthal and later the Denisovans, they found their genes hiding in our own. The quirky tidbit that has now become common knowledge is that if your ancestry is from outside of Africa, you have about 1 to 2% Neanderthal DNA in your cells. And if you have ancestry from Melanesia or Australia, you might have up to 5% Denisovan DNA. This discovery changed everything again. It meant that the replacement wasn't clean. It was leaky. As your Homo sapiens ancestors spread across the world, they didn't just outcompete their archaic cousins, they met them, and on some occasions they interbred with them. The strict replacement model was wrong, too. The modern synthesis is a hybrid of the two old ideas. Yes, we are overwhelmingly a species that came out of Africa recently, but we carry within us the genetic ghosts of the other human worlds we encountered along the way. So, in a small but profound way, the multi-regionalists were right. There was gene flow between different human populations across the globe. And this brings you back to Homo erectus. They were the ones who wrote the first draft of this story. They created the first global human network, the vast established population of archaic humans that your African ancestors would later meet and mingle with. They set the stage for the entire drama of the last 100,000 years. And a tantalizing question remains. Geneticists still argue about the possibility of interbreeding with even earlier hominins, including potential ghost populations of late surviving Homo erectus in Asia, whose DNA might still be present in tiny, fragmented amounts in modern human genomes. The search for that most ancient of human connections is still on, a hunt for the last, faintest echo of our 2-million-year-old ancestors in the code that makes you who you are. So you have walked this long, winding path, from the confusing family reunion of the first hominins, through the muddle in the middle, and into the complex, interconnected web of our own recent past. The story is not a straight line, but a braided stream. And now you must return to the question we started with, on that imaginary savannah 2 million years ago. Standing before this tall, dark-skinned, intelligent creature, what do you call it? Is it still just a clever ape? Or is it the first true human? After this journey, the answer seems to write itself in the dust. They are the first. They are the ones who drew the blueprint. You tick off the checklist of firsts, and it is a list of monumental achievements. They were the first to possess a body plan you would recognize as your own, with long legs and short arms, a body built not for the trees, but for striding across the horizons of the earth. They were the first to leave the cradle of Africa, their curiosity and adaptability carrying them across continents in a planetary expansion that had no precedent. They were the first to become systematic, cooperative, and terrifyingly effective predators of big game, fundamentally changing their place in the food web. They were the first to invent a complex, standardized tool that was not just an object, but an idea, a symmetrical form imposed onto stone by a thinking, planning, designing mind. They were the first to show the unmistakable evidence of compassion, of caring for the old and the weak, a social and emotional leap into a new kind of world. And they were, very likely, the first to tame a flame, and, without question, the first to scratch a symbolic, abstract pattern onto a shell, the very dawn of art. Their name, the mainstream historical fact given to them by Eugène Dubois, is Homo erectus, which simply means upright man. In a way, It's a name that is both perfect and wholly inadequate. While their bipedalism was the foundation upon which everything else was built, it sells their incredible accomplishments far too short. They were so much more than just the hominin that stood up straight. The quirky tidbit that underscores their global importance is the story of the Peking man fossils. Discovered in the 1920s and 30s in a cave at Zhoukoudian, China, these were among the most famous and complete Erectus remains in the world. But during the chaos of World War II, the original fossils were packed into crates to be shipped to safety in the United States and vanished, likely into the chaos of the Japanese invasion. Their whereabouts remain one of the great, unsolved mysteries of paleoanthropology, a lost treasure from our shared human heritage. You return to that final, closing analogy, the thought experiment that cuts through all the scientific jargon. Imagine you could step into a time machine and visit not just one individual, but a family of them, a small band of Erectus at the end of their day. You watch them from a safe distance. What do you see? You don't see a troop of apes. You see a human family. You see a hunter returning with food and sharing it. You see a mother comforting a crying child. You see an elder showing a youngster how to sharpen a stone flake. You see them communicating with a mix of sounds and gestures. You might even see them laughing. Despite the heavy brow ridges, despite the millions of years that separate you, their inherent humanity, their relatable personhood, would be obvious and overwhelming. The scientific evidence for this deep connection comes from the very rhythm of their lives, preserved in the microscopic structure of their teeth. By analyzing the growth lines on tooth enamel, which are laid down daily and seasonally like tree rings, scientists can reconstruct their developmental history. The data shows that Homo erectus had a slow, prolonged childhood, much like our own and unlike the rapid development of apes. This long period of dependency is a crucial human trait, the extended time needed for a large brain to learn all the complex cultural and technological skills necessary to survive. And so you are left facing the ultimate philosophical debate that their very existence forces upon us. What is the defining threshold for humanity? Is it a brain of a certain size? Is it the first stone tool? Is it language? Is it art? Is it compassion? The beauty of Homo erectus is that they make the question moot. They are the first ancestor who doesn't just check one or two of those boxes. They are the first to stride confidently across that threshold and check them all. They are the trunk of our family tree, the strong, stable, and enduring foundation from which all later, more fragile branches, the Neanderthals, the Denisovans, the Hobbits, and us, would eventually sprout. They are the original pioneers, the first draft of ourselves. You can feel their echo in your own bones. When you find yourself able to jog for miles on a treadmill, you are tapping into the legacy of the persistence hunter. When you sit down to a hot, cooked meal, you are honoring a tradition that began at a steaming hot spring or a crackling fire 1,000,000 years ago. A tradition that quite literally built the brain you are using to think these thoughts. Their spirit, that restless urge to see what lies beyond the next hill, that fundamental curiosity about the world, is the same impulse that would eventually push their descendants out of every valley, across every ocean, and ultimately to leave footprints on the surface of the moon. Their need for social connection, for family, for a tribe, is the very same need that builds our neighborhoods and our nations. They were the ultimate survivors. For nearly 2 million years, they were the face of humanity. They weathered the dramatic swings of the ice ages, survived supervolcanic eruptions, that would have plunged the world into darkness and adapted to landscapes from the tropical heart of Africa to the temperate forests of Asia. They were the sturdy, foundational stone upon which all the beautiful, complex, and sometimes fragile diversity of later humanity was built. They are the great, silent majority of our ancestral story, a testament to the power of endurance, cooperation, and the simple, world-changing genius of a well-made tool held in a capable hand. Their time on this planet is long since over. The sounds of their footsteps and their simple language have faded into the immense silence of deep time. And yet their story is not truly over, because their echo resides in all of us. Their ancient journey has not ended. It simply continues now, inside of you. And so the image of that ancient world, with its strange beasts and its vast, sun-bleached skies, begins to soften and fade from view. The sharp edges of the Handaxe, the heat from the volcanic pool, the distant call of the hunt. All of it now recedes, dissolving into the gentle, quiet darkness of your room. The long journey is over. What remains is the simple, reassuring truth of an unbroken thread. A chain of life that stretches back through all those countless generations, from your own sleeping form, through the Neanderthals and the Denisovans, through Heidelbergensis, all the way back to that tall, striding figure on the shore of an ancient African lake. You are the current custodian of a fire that was lit 2 million years ago, a legacy of survival and connection that is now written into every cell of your being. There is a profound and quiet peace in that knowledge, a sense of belonging to a story so immense that all the small worries of the day simply fade into insignificance. Feel the weight of that deep time, not as a burden, but as a comforting, heavy blanket. The story is finished. Now you can rest.